Yeah. Okay. Good morning to all. Actually, the class was scheduled at 6:30, but so I got information from 7 a.m. onwards. So there is some miscommunication gap. So yesterday we discussed that is from 7 a.m. only, 7 a.m. But so they have created the class 6:30. That's the reason. So I wrote here 7 a.m. onwards, but even I have joined at 6:30. Fine. Okay. Right. So I hope most of you have joined. Seems. Yeah. So yesterday, the last class, we have started that construction of alternator, and also we are completed that phase sequence of three-phase alternator. Phase sequence of three-phase alternator is the order at which maximum values of induced EMF. In which phase first maximum value, next in which phase, next in which phase. That is the phase sequence, maximum value of induced EMFs. We have seen phase sequences depends on the direction of field rotation. Phase sequences depends on the direction of field rotation or direction of armature rotation also. If rotor rotation reversed also, phase sequence changes, and even prime mover rotation is reversed, phase sequence will change. But phase sequence does not depend on the direction of the field current. Phase sequence is no way related with direction of field current. Similarly, synchronous motor also, direction of rotation can be reversed. Direction of rotation can be reversed by changing the supply phase sequence, just like induction motor. But if you change field current, there will be no change in its direction of rotation. But whereas DC motor, if you change the field current, direction of rotation changes, but synchronous motor is not going to be changes. Why it is like that, we are going to see later. Okay. At the time of synchronous motor, I am going to explain why it does not depend on the direction of field current. In our synchronous machine, dear students, please remember that in our synchronous machine, field current magnitude only important. Field current magnitude only important. Direction is least bothered. Because it is separately excited. No? We are separately exciting with the DC. Current is, direction is not a matter. Okay. Direction changes, what will happen? North becomes south, south becomes north. Right? But north pole and south pole are magnetically locked. At one particular instant, the opposite poles will lock. Okay. Yeah. And also we have seen magnetic drag, another concept, magnetic drag. So magnetic drag is a electromagnetic torque opposition in the case of a generator. In every generator, torque opposition takes place, that is electromagnetic torque that opposes the prime mover rotation. And that electromagnetic torque only itself load torque. Right? Yeah. And the torque can be represented in equivalent terms of power output. So power is equal to torque into omega. Okay? Yes. But omega is equal to TPM minus TEM by B. That relations we should remember. Okay. And later also we have started our construction of alternator. So construction of alternator based on the rotor construction, there are two types of alternator. Rotor construction, two types of alternators. What is that? One is salient pole synchronous alternator. Another one is cylindrical rotor alternator. But stator is common. And in salient pole synchronous motor, just we have gone through that. Salient pole synchronous motor, main the key point. Air gap is non-uniform. Air gap is more non-uniform. Okay. Air gap is minimum along the pole center and maximum along the quadrature axis, interpolar axis. But for production of the sinusoidal flux distribution, always we should get flux density wave is sinusoidal. We have to design our alternator for obtain the flux distribution is sinusoidal. When flux density wave, B wave is sinusoidal, then generated EMF will be sinusoidal. In salient pole machine, flux distribution can be made sinusoidal. B can be made sinusoidal by chamfering the salient pole. Chamfering means minimum air gap along the pole center and air gap is increased towards the pole ends. And the chamfering is proportional to sin theta, inversely proportional to cos theta. Okay. The air gap is changed with the sin theta. Then you will get flux distribution will be sinusoidal. Okay. Then there is no harmonics. And also we have seen another important points, because construction, each and every point is important. Okay. And they are said to be low speed alternators. No, they cannot be driven at high speeds. Projecting nature, one pole projecting nature, high speeds, centrifugal forces. Every rotating machine will have centrifugal forces, it cannot withstand. So those type of rotors to be driven only at low speeds, no? Low speeds. That's the reason they are said to be low speed alternators. Of course, the suitable turbines are low speed turbines. There are various types of turbines are there. Steam turbines, gas turbines, okay, hydro turbines. But hydro turbines are best suitable for, right, to drive the salient pole alternator. Hydro alternator. Because water turbines are designed for low speed. They are better suitable. And they can also be used for diesel engine. Right? But since they are low speed means more number of poles, larger diameter is larger, but length must be smaller for a given rating, for a given power. Okay. Up to this point we have closed yesterday. Now we just started that damper winding. So let me continue with that damper winding. Damper winding. We were discussing about damper winding. And damper winding can also be called as amortisseur winding. Amortisseur winding. Damper winding or can be called as amortisseur winding. The damper winding is made with copper. Damper winding is made with copper and that can be kept on the rotor pole shoes, slots made under the pole shoes. Okay, just let me draw this. Damper winding, our salient pole machine. Now, once again, I am drawing. For a 4-pole machine, I will draw very quickly. This is salient pole rotor, na? Yes. On this, we kept field winding. On this field winding. Here I am drawing blindly, excited with DC. Okay. Based on the current direction, of course, this is acting as a north pole, this is acting as south pole, north pole, south pole. And where damper windings can be kept, damper windings can be kept. Damper windings are kept on the slots made under the pole shoes. Slots made under the pole shoes. The damper winding, I am adding the damper winding with red color. They are kept slots made under the pole shoes. We'll cut that portion and in that the damper winding can be kept. Damper winding made in the form of copper bars. They are not small wires, thick bars. These are the damper bars. Damper winding in the form of bars. They are kept under the slots made under the pole shoes. When the slots are there, there we will cut that portion. In that we will keep the damper winding. And they are short circuited on both ends at end rings. And this damper winding is totally short circuited on both sides with the end rings. These are end rings. And this side also we will short circuit. Totally both will be short circuited with end rings. Right? Yeah, these are said to be end rings. With the end rings we will short circuit. This is damper winding. It looks like squirrel cage rotor of induction motor. No, damper windings, it looks like squirrel cage rotor of induction motor. Because in squirrel cage also total winding is, rotor winding is short circuited, na? Yes. They are also in the form of bars. So in alternator, how many windings will exist? One winding that can be kept on the stator, that is the main armature winding, no? Is armature winding. And another one is field winding. Third one is damper winding. So in salient pole synchronous machine, there will be three windings. Armature winding, that is the main winding in that EMF is induced. Second one is field winding. What for field winding? To produce the flux. It will create the poles. Damper winding is another one. So damper winding is made with copper bars. Copper in the form of bars. They are inserted in the slots made under the pole shoes, and they are short circuited at both the ends with end rings. Yeah. Let me write that point. Damper winding is made with copper. In the form of bars. They are in the form of bars. Made with copper. They are in the form of bars. Not small wise. Not thick bars. In the form of bars. And inserted in the slots. Made under the pole shoes. And they are short circuited at both ends. At both ends with end rings. They are short circuited with end rings. These are said to be end rings. Okay. Yeah. These are the end rings. And these are the damper bars. Okay. Yes. In the form of damper bars. In our examination, how they can ask? So last year also he has asked compensating winding, damper winding, squirrel cage winding. You want to check the construction point of view. So the damper windings are placed where? Under the pole shoes or in the stator core or in the rotor periphery. It can be kept on the slots made under the pole shoes. Okay. Now, what is the function of the damper winding? Why to keep? What is the necessity of damper winding? Function of the damper winding. Let us see. Function of the damper winding. Function of damper winding. What is importance of damper winding? Damper winding is number one, in alternator, its function is To eliminate the hunting, number one, to eliminate the hunting, each and every point is important. Dear students, construction, on that you will get most of the times one question. And we are going to see each and every point. In alternative, to eliminate hunting, eliminate the hunting. Hunting means that is rotor oscillations. Rotor oscillations. To eliminate the hunting. And to suppress the negative sequence field. And to suppress the negative sequence field. Negative sequence field. This is in the case of alternator. And in the case of motor, synchronous motor. The case of synchronous motor, because construction is same, na? Synchronous motor, because same machine can be used as a motor and generator. Same machine can be used as motor and generator. And in synchronous motor, it is to eliminate the hunting. To eliminate the hunting. And second one is to for starting purpose. For starting purpose. To eliminate the hunting. And second one is for starting purpose. And as you may be knowing, synchronous motor is not self-starting. Synchronous motor is not self-starting. One of the starting method is damper winding starting. Damper winding, like induction motor starting. Damper winding looks like induction motor winding, na? Yes. But primary function, what is the primary function? Whether it may be acting as generator or motor, primary function is to eliminate the hunting. Okay. And secondary function to suppress the negative sequence field. Negative sequence means harmonic field. The fifth harmonic field will produce the torque in opposite direction. Yes. But fifth harmonic torque also, fifth harmonic, it can be eliminated by suppress. It will suppress the negative sequence field. Fifth harmonic field can be suppressed by the damper winding also. Negative sequence, not only fifth is negative, seventh is positive. That can also be eliminated. And secondary function is for starting purpose. But primary function of damper winding to eliminate the hunting first, and in motor and generator. And first of all, what is hunting? Hunting is rotor oscillations. Hunting is nothing but rotor oscillations. This hunting takes place only in synchronous machine, no? Only in synchronous machine, no other machine. Is there any hunting in the case of induction motor? No, there is no question of hunting in the case of induction motor. It is only in synchronous motor, synchronous generator. Why? Why? Because synchronous machine has to rotate only at synchronous speed. Only at synchronous speed. Then only unidirectional torque will be developed. Unidirectional torque will be developed. So for example, see, this is our stator core. This is our stator. And rotor, say for example, this rotor. Salient pole rotor. I am taking front view. Based on the current direction, say this is acting as a north pole. This is north pole. Say this is south pole, north pole, south pole. Field winding can be kept, of course. We are keeping field winding on this. We are keeping field winding on this. So based on the current direction, one act as a north pole, one act as a south pole. Okay. Now don't worry about every time applying the right hand rule, all those things. Right? Yeah. But when machine is connected on the bus bar, dear students, remember that hunting takes place only when the synchronous machine is connected on the bus bar. Motor always connected on the bus bar. But generator, there are three cases. Generator, single alternator, two alternators in parallel, alternator connected to the grid bus bar. So, first let me ask a question. Is there any hunting for a single alternator? Single and one alternator, like your laboratory. Only one alternator is there. Okay, one load is there. One prime mover. It is not connected to the grid. Only single alternator supplying a load with one prime mover. Is there any case of hunting? Nothing. Loss of synchronism? No. For a single alternator, no loss of synchronism. Okay, no loss of stability. No hunting, nothing. Because when load increases, what will happen? When load increases, your machine speed decreases. Alternator speed decreases. When speed decreases, its frequency decreases. If you are accepting, your load is accepting, nobody will bother. Nobody will bother. There is no loss of synchronism. So only when load increases, it will reduce with the rotate with reduced speed. 1500 RPM, load increases, it will rotate 1400 RPM. That 1400 RPM also you can call as a synchronous speed because that is related to your frequency. No loss of synchronism, nothing. But when machine is connected to the bus bar, say bus bar frequency is constant. When bus bar frequency constant, your alternator frequency also must be same. Must be same. If deviate means then loss of synchronism takes place. Motor always connected on the bus bar. See, for example, this is the motor. Motor is connected. When motor is connected, there three-phase winding. We will keep three-phase windings na? R dash, right? Y dash, and B dash. Three-phase winding we will keep. Then based on the three-phase windings, what will happen? If it is a motor, it will draw the current. Draw the current. Generator will deliver the current. Generator will give the current. Motor will take the current. But whether it is taking or giving, there will be poles will form. Stator poles, rotating magnetic field, RMF, induction motor, just like induction motor. See, stator of induction motor, stator of synchronous motor, stator of induction generator, alternator, all that same. There is no difference. Three-phase machines now all there. So stator winding, they are 120 degrees spatially displaced, and they are carrying the currents. Okay. So therefore, in generator also rotating magnetic field is produced. Motor also rotating magnetic field is produced. Just like induction motor, synchronous motor, alternator also same. RMF is perfectly same. So when it is acting, motor or generator, see first I am explaining for motor. This is you are giving based on the current direction, say south pole, rotating magnetic field will form. This is south pole, this is north pole, south pole, north pole, say RMF, rotating magnetic poles, and they will rotate at synchronous speed. So for example, they are rotating at 1500 RPM, say. It's a synchronous speed for 50 Hz frequency, 1500 RPM. They are rotating at synchronous speed. Now, due to magnetic locking between these two, your rotor also will rotate at 1500 RPM. Rotor will rotate 1500 RPM. Therefore, south pole and north pole, due to magnetic locking, both will rotate together. Both will rotate together. Right? Yes. Steady state condition. But due to any reason, if load suddenly increases, say, on synchronous motor, suddenly increases load, or generator, electrical load is suddenly increases. When load suddenly increases, speed is going to be reduced, rotor speed reduces. Rotor speed, if it is 1400 RPM, say, if it is 1400 RPM, now can you tell me, is the south pole of the stator is existing under the north pole? No. South pole do not exist because south pole is faster, stator poles are faster. When stator pole is faster means after some time, this pole will go to here. After some time, this pole may go to here. South pole may come to here. South pole may come to here. But this north pole will comes under this north pole after some time. This is coming because these poles are faster, na? Yes, this pole is rotating at 1500 RPM. After some time, definitely north pole also will comes under the north pole. North pole. Then what it will do? It will repel. It will repel. Earlier, south pole was there. Under north pole, south pole, it is torque is developing in clockwise direction. It is attracting the south pole. But when your rotor pole is slower, the south pole went somewhere, and another north pole is coming, and the same pole is coming, and then it will repel. Rotor oscillate due to that, right? Torque pulsation, because both rotate together. I hope this point is very simple, dear students. Listen once again. When south pole of the stator, north pole of the rotor, both rotate together with the same speed, steady state condition. At that time, no hunting, nothing. But when your rotor is slower, means these poles are moving faster. Then under north pole, not always exists south pole. South pole is going faster. Then next north pole will come. Then it will repel. So like that. Again south pole will come, attract. Again north pole will come, repel. Because relative speed is there now. So due to that, north pole do not existing under the south pole. So it is subjected with clockwise torque and counterclockwise torque, so that the machine will oscillate. That rotor oscillations are called hunting. If the rotor oscillations exceeds beyond a particular value, loss of synchronism takes place. Loss of synchronism. It is same in the case of generator also. I am of course explaining motor. Generator also it will be same. Generator we will rotate with the prime mover. We will rotate with the prime mover. If electrical load increases, then prime mover speed also reduce. Then rotor is slower. Okay? Whenever if rotor rotate other than synchronous speed, not synchronous speed, no hunting. If rotor speed decreases, if it may be increases also, then hunting takes place, rotor oscillation takes place, right? But these rotor oscillations can be eliminated by using the damper winding. And first of all, what are the causes for hunting? Why hunting is taking place? Causes for hunting. The important thing is causes for hunting. Let us see. What are the causes? Causes for hunting. Causes for hunting. Number one, sudden change in load, disturbances. Sudden change in load. Second one, sudden change in supply system. Sudden change in supply system. Third one, sudden change in field system. Sudden change in field or that is excitation system. Field system. Fourth one, load containing harmonic torques. Load containing harmonic torques. All these are the reasons. Load containing harmonic torques. Sudden change in load. Sudden change in supply system. Sudden change in field system. Load containing harmonic torques. Okay. Load containing harmonic torques means that is intermittent loads. They are called what? Intermittent loads. Intermittent loads like punching machines or cutting machines. All these are the reasons. Sudden change in load, sudden change in supply system, sudden change in field system, load containing harmonic torques. Sudden change is nothing but disturbance. Dear students, change in load is not disturbance. Definitely load can be changed. You can operate at a half load, full load, or load can be changed. Practically loads are not constant. Load may changes, but sudden change in load is disturbance. Load can be gradually, you need to change, not suddenly. Generally, how you can change the load, tell me? Load, how you can change? When load increases, prime mover input also you have to increase. Then there is no hunting. These things you can see from this relation. Omega is equal to prime mover torque minus electromagnetic torque. Correct? This we have seen. Divided by B. Omega is equal to TPM minus TEM divided by B. So, for example, if load is suddenly increased, say electromagnetic torque increases. Alternator. Electromagnetic torque increases means speed will reduce. When rotor speed reduces, then it will tend to oscillate. Rotor speed decreases. Rotor will clockwise, counterclockwise, because under north pole, south pole will come, attract. And again under north pole also will come, repel. So rotor will oscillate. Sudden change in when load suddenly increases. Even motor also, mechanical load suddenly increases, rotor will tend to oscillate. Right? Second one is sudden change in supply system. Sudden change in supply. Supply system means what? For alternator, what is the supply? Prime mover input. But suddenly more water is given. For example, governor system will be there. Na? Governor means there will be valves. If you open the valve suddenly, more water, more heating, prime mover torque increases, rotor accelerate, rotor speed increases. Correct? Rotor speed increases. Or suddenly you close the valve more, input is given less, then rotor will decrease. Okay? Sudden change in prime mover torque also. If you change prime mover torque also suddenly, rotor may decreases or increases. That also subjected with oscillations. Sudden change in supply system. And even for motor, what else? Prime mover, sudden change in prime mover torque also. Okay. Not only sudden change in voltage also. Sudden change in voltage. Voltage changes. For motor, supply voltage is suddenly, voltage fluctuations are coming now. Then it is also subjected with oscillations. Voltage. Okay. Yes. When voltage changes, V by F ratio changes. Flux changes. When flux changes, TEM is proportional to flux into current. Na? Yes, TEM is proportional to flux into current. And when V suddenly changes, V by F ratio changes, flux also changes. And even frequency changes also. Sudden changes, all these are the, when prime mover torque changes, voltage changes, frequency changes, all these are also causes hunting. Okay. You should remember each and every point. In one particular examination, he has given the question like this. The question is like this on this. Which of the following is not the reason for hunting? Not the reason for hunting. Which of the following is not the reason for hunting? A will. Sudden change in load. B will. Sudden change in voltage. C will. Sudden change in frequency. D will. Friction and windage losses. This is your examination question. Friction and windage losses. Now, tell me what is the answer? Which of the following is not the reason for hunting? Not the reason for hunting. So what is your answer? Your answer will be friction and windage losses. But all other things are reasons only. Change in load also, change in voltage, change in frequency. All these are the reasons. Okay. But which is more common? Sudden change in load is more common, of course. Other things also reason. And even sudden change in field system also. The excitation, field current suddenly changes, flux changes. Na? Flux changes. When flux changes, torque, electromagnetic torque changes. When suddenly flux changes, say, electromagnetic torque also changes. Electromagnetic torque changes, speed changes. Sudden change in field, excitation suddenly changes also will take place. And load containing harmonic torques. Load containing harmonic torques means some type of loads are there, na? They are intermittent loads. Intermittent means load suddenly changes, load falls, load release. Intermittent means like cutting machines, punching machines, cutting. If you want to cut, a sheet is there, okay, or laminations you want to cut. How you can cut it? So a cutting tool will be driven by a motor. It will be hit on that a sheet. It will cut. For example, you want to prepare a shape of the car doors. For example, car is there, right? Car doors, you have to prepare in a particular manner. There will be punching machines only. Whatever the shape of car door you want, a metal sheet will come, it will be hit on that. So that portion will cut and will come up tool. Cutting tool will come up. Another sheet will come, again hit. Again it will come up, another sheet. It is continuous process, cutting machine. But there what is happening? While hitting it is load operation. While coming up, load release. Load falls, load release. It is having load operation, no load operation. That is intermittent loads. But finally, what the motor will observe? Load, no load. Load is suddenly falling, suddenly falling. Then also it is subjected with hunting. It is nature of the load, of course, is not disturbance, but load is itself like that. Such type of loads is used, then also hunting takes place. Fine. All these are the causes. But how effects of hunting? What are the various effects of hunting? What are the problem with hunting? Effects of hunting. Effects of hunting. Effects of hunting. Yeah. Due to rotor oscillations, stresses will be developed in the rotor shaft. Stresses will be developed in the rotor shaft. Mechanical stresses. So lifespan of the machine will reduce. Yes. Number one, first one is due to rotor oscillations. Effect of hunting, or that is rotor oscillations. Effect of rotor oscillations. When rotor is continuously oscillate, what will happen? Right? Due to rotor oscillations, the rotor shaft. Due to rotor oscillations, the rotor shaft, mechanical stresses are developed in the rotor shaft. Mechanical stresses are developed. Mechanical stresses are developed in the rotor shaft. The rotor shaft and fatigue of the rotor. Fatigue of the rotor. Rotor will fatigue. Fatigue of the rotor. Mechanical stresses are developed in the rotor shaft. Definitely lifespan is going to be reduced. Lifespan is going to be reduced. Number one. And second one is due to fluctuations, voltage fluctuations are there. Due to voltage fluctuations, what will happen? Rotor oscillations, voltage fluctuations. Due to rotor oscillations, voltage fluctuations. Voltage fluctuations of alternator. Because when rotor oscillate, rotor speed decreases, increases, say voltage fluctuations. Therefore, there is a loss of choice of voltage stability. Therefore, choice of loss of voltage stability. Voltage stability. Right? Next, third one is due to rotor oscillations, losses in the rotor. Losses in the rotor. Therefore, heating effect. Heating effect. Due to variations, frequency variations, what will happen? Iron losses also developed in the rotor core. Mechanical losses also. Losses in the rotor. Heating effect. Heating effect. Fourth one, there is a loss of synchronism. Choice of loss of synchronism. Choice of loss of stability or synchronism. All these are the effects. All these are the effects. All these 4 points are being given in the IES examination, ESC examination. All 4 statements out of this, which is correct? All these are correct. I think you are knowing multiple select answers are there, na? MSQs, multiple select questions. You will give 4 statements. Among the 4 statements, which statement is correct? Which statement is correct? Because last year onwards, they were introduced this MSQs, and he is checking the theoretical knowledge of the student also. Do the student is having idea about that content or not? Earlier, maximum numericals, no? Maximum numericals. But some questions also is giving in terms of MSQs, multiple select questions. In single question, he will ask only single answer, na? But here, whether student is having idea about all the statements or not. Okay, fine. These are the effects of hunting. Effects of hunting. But how to eliminate the hunting? Elimination of hunting. Let us see. Elimination of hunting. Elimination of hunting. How hunting can be eliminated? Elimination of hunting. Yeah. Let me go for the next page. Elimination of hunting. How hunting can be eliminated? Elimination of hunting. Number 1, by using flywheel. By using flywheel. Second one, by designing the machine. By designing the machine such that having suitable synchronizing power coefficient. Suitable synchronizing power coefficient. By designing the machine such that having suitable synchronizing power coefficient. Third one is by using damper winding. By using damper winding. Remember that all these are the reasons, causes. There is a methods to eliminate hunting. By using flywheel. By designing the machine such that having suitable synchronizing power coefficient. And by using damper winding. Damper winding. All these are the reasons. Yeah. But flywheel is very old method. No? Flywheel is not generally used. Method is available. Okay. Flywheel. It will not allow sudden changes in speeds. Correct? So for example, a rotor is there. Is a rotor. Of course, it may be salient pole rotor or cylindrical rotor, whatever it may be. General case. A rotor. To this, a large flywheel is attached. Large flywheel having large moment of inertia. When that, due to large moment of inertia, it will not allow sudden changes in speed. This is a flywheel. This is a flywheel. Correct? Flywheel. Will not allow sudden changes in speed. Will not allow sudden changes in speed. Sudden change in speed. Okay. What is Satya Anusha? You are raising your hand. Satya Anusha, please tell me why. Hello, Satya Anusha, tell me. Hello. Satya Anusha. Okay. I will come to your doubts because yeah, tell me, Satya Anusha. What's your doubt? Are you there? Unmute and you can ask. Right. Okay, any doubts are there? Please, we can ask later. In between the class means I cannot able to attend all that. So it will cause us a bit disturbance now. Fine, no problem. So large moment of inertia, due to large moment of inertia, what will happen? It will not allow sudden changes in speed. But making the smoothing the speed, a big flywheel will be attached. It will not allow sudden changes in speed due to large moment of inertia. I think you will be knowing the flywheel concept is, if load is suddenly increased, say it release the energy. When load is suddenly decreased, it absorbs the energy. When load is decreased, means it will absorb the load. It will act as a load. But when load is suddenly increases, it acts as a source. Because the beauty of inertia torque, Ti is equal to what? J d omega by dt. The inertia torque changes. When d omega by dt is increasing order, say inertia torque is one direction. If speed decreases, torque direction changes. D omega by dt is negative, na? Yes, torque direction changes. But this is not that much important to discuss here. Unnecessary waste of time. So only method is available. So you may be knowing already. For smoothing the speed, flywheel will be used. It's a mechanical system. But alternators practically, it is a large alternator, large flywheel. It is unnecessarily causes space occupation and vibrations unnecessary. Right? So method is available. You just have idea about. Okay. And second one is by designing the machine such that having suitable synchronizing power coefficient. So this again we are going to see next separate topic. PSY, synchronizing power coefficient, is called dP by d delta, dou P by dou delta, derivative of the power. This topic again we are going to see before parallel operation of alternator. Right? In the fifth chapter we are going to see synchronizing power coefficient, separate topic, separate reading, we will see. But that is also possibility. Mainly let us focus by using damper winding. How hunting can be eliminated. This is very important for your examination point of view. Okay. So let us focus by using damper winding, how hunting can be eliminated. Okay. See, damper winding. How damper winding acts as I have shown now? Yes. Damper winding, with respect to damper winding, rotor behaves as squirrel cage rotor of induction machine. Squirrel cage rotor. With respect to damper winding. Squirrel cage rotor also, the winding can be kept on the rotor periphery. They are in the form of bars. They are totally short circuited, na? Squirrel cage rotor, yes. So here also damper winding, it acts like a squirrel cage rotor. And stator is same as that of induction motor. Stator of, for example, this is our synchronous machine stator, say. Machine is connected on the bus bar. Machine is connected on the bus bar. Maybe motor or it may be generator. Motor we will connect mechanical load. Generator we will connect the prime mover. I am not showing the prime mover here. Prime mover. But when machine is connected, generator what it will do? It will deliver the currents. What about motor? Motor it will draw the current. That's all. It will draw the current. But whether three-phase winding, balanced winding, three-phase winding is balanced winding. Winding can be kept. Armature winding, this is armature winding. All these are armature winding. If R phase is kept here, R dash can be kept here. Y phase here, Y dash will be here. B phase here, B dash. That is itself armature winding. A stator winding you can see. In synchronous motor, sorry, induction motor, stator winding. Here stator winding is also same. But the stator we are calling is armature winding separately. Okay, stator winding, same as that of induction motor. And that stator winding also three-phase windings, they are displaced 120 degrees spatially. And a phase displacement is there. The currents will have phase displacement. Rotating magnetic field will be produced. Rotating magnetic poles, stator poles. Here stator poles will form, na? Yes, stator poles. Say this is south pole of the stator. This is south pole of the stator. The south pole will rotate at synchronous speed, say. The south pole of the stator rotating at synchronous speed, some 1500 RPM. Synchronous speed 1500 RPM I am taking. And this is north pole of the rotor. This also will rotate at 1500 RPM. 1500 RPM steady state condition. Steady state condition. And when both are rotating due to magnetic locking, both are rotating at synchronous speed, say, there is no oscillations. Torque is same direction. South pole of the rotor always attract the north pole of the rotor. So torque will be developed. Torque is developed. Fine. That is steady state condition. And see, stator is same as that of the induction motor. With respect to damper winding, rotor also same as that of induction motor. Why I am saying again repeatedly induction motor means the damping torque developed. Damping torque developed is based on the induction principle. When rotor deviate, when rotor right speed is less or more than synchronous speed, induction machine action will comes into picture. Induction machine action will comes into picture. If rotor speed is less than synchronous speed, induction motor action will comes into picture. And when synchronous speed, rotor speed is more than synchronous speed, induction generator action will comes into picture. So with respect to damper winding, it acts as like a squirrel cage rotor of induction motor. Stator is same as that of induction motor. Synchronous machine also stator is same. Therefore, rotor with respect to damper winding, when rotor speed increases or decreases, induction machine action. Right? Less than synchronous speed means motor action, more than synchronous speed, generator action will come into picture. Fine, yes. And of course, you may be knowing when induction motor, what is the direction of torque? In motor, torque, electromagnetic torque developed will be in the same direction of rotor rotation. Same direction of rotor rotation. But in generator, torque will be in opposite direction. Every generator, torque developed will be opposite direction. Because damper winding will develop the torque. Rotor winding, damper winding will develop the torque. Induction motor, same direction it will develop. Generator, opposite direction. Yesterday we have seen the magnetic drag. Every generator torque will be opposite direction. But every motor torque will be same direction. I think you may be knowing this statement, very famous statement. In motor, torque support the rotation. In the motor, torque support the rotation. Whereas in generator, torque opposes the rotation. Opposes the rotation. But motor torque support the rotation. Because in motor, torque is first. No? Torque is first. Then only motor rotate. Torque support the rotation. Okay. So let me write these points. With respect to damper winding, the rotor behaves as squirrel cage rotor of induction motor. Squirrel cage rotor of induction motor. Okay. Stator is also same as induction motor. Stator also same as induction motor. Therefore, when the rotor speed deviate, when the rotor rotate other than synchronous speed, during hunting, speed increases or decreases other than synchronous speed, induction machine action will comes into picture. Induction machine action will comes into picture. Induction machine action will comes into picture. When rotor speed is more than synchronous speed or less than, when the rotor speed NR, if NR is less than NS, then induction motor action. But when NR is more than NS, induction generator action takes place. More than synchronous speed, generator action. Less than synchronous speed, motor action will comes into picture. Okay. Yeah. But when NR is equal to NS, no induction machine action. When NR is equal to NS, no induction machine action. When NR is equal to NS, say no induction machine action. No induction machine action. When rotor speed is more than or less than synchronous speed only, it will comes into picture. Okay. Now let us see one by one. When load is suddenly increases, see, when load is suddenly increases, rotor speed will decrease. Rotor speed will decrease. Listen. I hope you have taken, huh? Yes. See here, when rotor speed, see, are you coming to here? Yes, listen. This is stator poles always rotated 1500 RPM. Dear students, stator poles is nothing but what? Rotating magnetic field. The stator poles always rotating with constant speed. Why? Because stator RMF, constant speed. Reason is, it is connected on the bus bar. Na? Bus bar means NS is equal to 120 into F by P. F by P. If F is constant, say, F is constant, therefore NS also constant. NS is constant. And rotating magnetic field, because stator is connected to the grid, say, grid frequency constant, F is constant. Then rotating magnetic poles. The stator poles rotate constant speed only, RMF. That is called rotating magnetic field, rotating magnetic poles. Stator poles rotate constant speed. And stator flux. Stator flux is called what? Armature flux. Armature flux, rotated synchronous speed. This is south pole of the stator, north pole of the stator, and this is south pole, north pole. No. This is north pole, this is south pole. Because there are also 4 poles, na? 4 poles. 4 poles. Yeah. Then what is the direction of armature flux? Tell me. Stator flux. Flux is nothing but armature means stator flux. The direction of armature flux is like this. Flux will be from north to south. Armature flux, it will passes north to south. It will take return path like this. Return path. And similarly, this north pole to this south pole. South pole. Similarly, this north pole to this south pole, this side. North pole to south pole. What I mean to say is, stator flux crosses the air gap or not? Yes. Stator flux crosses the air gap. So, stator flux cuts by the rotor winding. Just like induction motor, stator flux, armature flux cuts by the damper winding, rotor conductor, when rotor deviate from synchronous speed. Rotor deviate from synchronous speed. Okay. Yes. Listen. I am going to write each and every point. First, you focus on this. Dear students, see, when your rotor is rotating, when stator flux is 1500 RPM, that is fixed. And when rotor is also rotating at 1500 RPM, there is no relative motion between the armature flux, stator flux and the rotor winding. There is no relative speed between the stator flux, armature flux, armature flux, and damper winding. Because rotor damper winding is kept on the rotor. So stator flux is rotating at synchronous speed, damper winding also rotating at synchronous speed. There is no relative motion, therefore no flux cutting action. Damper winding is not cutting the flux. No induced EMF in the damper winding, therefore no torque. No induced EMF, no current, no torque. No torque. Machine is said to be steady state condition. Therefore, steady state condition, no function of the damper winding. Not required because machine is all right. Machine is steady state condition, induction machine action will not come. Okay, yes, it is steady state. But when load is suddenly increases, say, when load is suddenly increases, what will happen? Rotor speed decreases. Rotor speed. For example, this rotor speed is 1400 rpm, say 1400 rpm. Stator flux 1500 rpm, but rotor flux 1400 rpm. Then relative speed is there, na? Relative speed 100 rpm. Rotor is slower, 100 rpm. Due to that relative speed, what will happen? It cuts the magnetic flux. Rotor winding, damper winding cuts the armature flux, stator flux. When flux cutting action means induced EMF in the damper winding. When induced EMF is there, then again torque will be developed. Induced EMF means current. They will drive the current in the damper conductor. Damper current will maintain. They will maintain the damper current. Damper current. Due to the damper current, damping torque will be developed. Damping torque is proportional to TD is proportional to armature flux and damper current. Armature flux and damper current. This damping torque is equal to armature stator flux, rotor current. Na? Torque is nothing but stator flux, rotor current. Stator flux is armature flux, damper current. So finally it is like this. When rotor rotated less than synchronous speed, damper winding cuts the armature flux, EMF is induced. When induced EMF is there, damper winding path is closed. Path is closed. So the induced EMF in the damper winding will drive the current. And this damper current interact with the armature flux. Damper current interact with the armature flux will develop the damping torque. But the damping torque is it induction motor torque or induction generator torque? When rotor speed is less than, then it will be induction motor torque. Induction motor torque in which direction? Tell me. Induction motor torque will be in the same direction of rotor rotation. Motor torque, same direction. So due to that, in same direction means now rotor is going to be accelerate. It is 1400 rpm rotating the rotor, 1400 rpm. But damping torque extra is coming. That also in the same direction. Due to that, rotor accelerate. Rotor accelerate and finally reaches to synchronous speed. This finally reaches to synchronous speed. But yes, mean to say when rotor speed is, when rotor, see this is armature flux, na? Yeah, this is armature flux rotating at 1500 rpm. This is always stator flux 1500. And when rotor NR is equal to is 1400 rpm, say 1400 rpm means now damper winding cut the flux, EMF is induced. Then damping torque will develop. This damping torque will be, damping torque is induction motor torque. Which direction? Same direction of rotor rotation. Same direction of rotor rotation. Then rotor will accelerate. Rotor speed accelerate, sorry, not in the same direction, I'm sorry. In the same direction, not opposite direction. Induction motor torque in the same direction of rotor rotation. Then the rotor accelerate, finally reaches to synchronous speed. Synchronous speed. When NR is less than NS. Less than NS. But when NR is more than NS, what will happen? Tell me. When NR is more than NS, rotor rotate more than synchronous speed. So this is stator field is 1500 rpm, but rotor is rotating some 1600 rpm. 1600 rpm. Then also rotor cut the armature flux. Rotor cut the stator flux. EMF is induced and current. And that current interact with armature flux will develop the damping torque. The torque is induction generator torque. Rotor speed is more than synchronous speed, generator torque. Which direction? Opposite direction. It means when this is phi A rotated 1500 rpm, but when NR rotor speed is equal to some 1600 rpm, say 1600 rpm, more than synchronous speed, the torque developed will be induction generator torque. The damping torque is induction generator torque. Induction generator torque. Due to that, rotor will decelerate. The braking action, it is rotating 1600 rpm, but torque is coming. The rotor torque is developed opposite direction. Due to that opposite direction, rotor will decelerate. Rotor speed decreases and reaches to synchronous speed. Opposite direction, right? And speed will be decreases and finally reaches to synchronous speed. If when NR is equal to NS, say what will happen? If NR is equal to NS, Armature flux is also 1500 rpm. It rotates always 1500 rpm. But when NR also equal to 1500 rpm, then damping torque is equal to 0. No damping torque, because machine is steady state condition. Once it is reached steady state condition, or it is at steady state condition, damper winding, no function of the damper winding, because no relative motion, slip 0. Stator flux 1500, rotor also 1500, both are synchronous speed, no relative motion, no EMF, no current. No current means no damping torque, not required. Damping torque will be 0 at that time. Okay. So it is quite simple. In your examination, what type of question they will ask now, you can go and see. GATE or IES examination. And damper winding question is quite direct questions. Direct question is, when rotor speed is more than synchronous speed, when rotor speed is more than synchronous speed, the torque developed in the damper winding. A bit, induction motor torque, B bit, induction generator torque, C bit, reluctance motor torque, D bit, some other torque. What is the torque? The torque will be induction generator. When rotor speed is more than synchronous speed, generator torque, induction generator torque, less than induction motor torque. Only induction machine action only will comes into picture. Induction machine action only when rotor deviate from synchronous speed. Okay. Yeah. Now let me write all these statements. See, when rotor speed is more than synchronous speed, when NR is less than NS, whatever I was explained, I am writing. When NR is less than NS, the induction motor torque is developed. Induction motor torque is developed. In the same direction of rotor rotation. In the same direction of rotor rotation. Same direction of rotor rotation. Then the rotor accelerate. Finally reaches to synchronous speed. Finally reaches to synchronous speed. Okay, synchronous speed. Next term, when NR is more than NS, when NR is more than NS, then the induction generator torque is developed. Induction generator torque. Generator torque is developed. Torque is developed in the opposite direction. In the opposite direction that of rotor rotation. Because in generator torque opposes the rotation. Yes. In the opposite direction that of rotor rotation. Then the rotor decreases. When the rotor decelerate and finally reaches to synchronous speed. Okay. Yes. Synchronous speed. But when rotor rotated synchronous speed, no relative motion, no induced EMF, no current, hence no torque. Machine is steady state condition. Machine is under steady state condition. Okay. When NR is equal to NS, when NR is equal to NS, when NR is equal to NS, there is no relative motion between. There is no relative motion between armature flux, that is stator flux and damper conductor. And damper conductors, damper windings. Therefore, no induced EMF, no induced EMF, and no current, no current. Hence, no torque. Hence, no torque, no torque. The machine is under steady state condition. The machine is at steady state condition. Steady state condition. Steady state condition, no induction machine action comes into picture. Okay? Yeah. So only important thing you need to remember, direction of the damping torque. Damping torque. Induction motor torque. Okay? But this is induction generator torque. Opposite direction. Opposite direction. Yeah. Of course, here I have taken 100 RPM difference, but damper winding do not wait until 100 RPM. Just 10 RPM changes, immediately it will come into picture. Instantaneously it will come into picture, so that always it will keep the rotor at without any oscillations it will rotate. We suppress the oscillations. We suppress the oscillations. Okay? Yeah. Of course, hunting, it can be explained with swing equation. Swing equation that I am going to explain at the time of mains examination for ESC students. Swing equation. But here, again, it will take a lot of time. Unnecessary. No equations are required. No? Directly conclusions I am giving. But whatever I am writing on the board, each and everything is individual objective question. Remember that. Okay. Yeah, now. So let me add 1 or 2 questions so that direct questions are there on the board. As the statements are questions. But how indirect questions will be given? Indirect questions. Let me give one question. Your previous GATE examination question. See, GATE 2016 examination. The question is like this. Tell me the answer for this. That is GATE 2016 examination question. The question is, in salient pole alternator, the hunting is predominantly reduced by A bit stator copper losses, B bit rotor copper losses, C bit stator iron losses, D bit friction and windage losses, Tell me what is your answer for this. Stator copper losses, rotor copper losses, stator iron losses, friction and windage losses. Tell me answer for this. Your chat box. Yes, what is the answer? Answer is rotor copper losses. Hunting is predominantly reduced by damper winding. Damper winding is made with copper that is kept on the rotor. So when damper current is there, rotor copper losses takes place. Answer will be indirect question. Rotor copper losses, no? Because damper winding is kept. Damper winding is made with what? Copper. Copper. and kept in the rotor, no? Kept in the rotor. Therefore, rotor copper losses. Rotor copper losses. Rotor copper losses. And I hope those who are completed induction motor, torque developed can be written in terms of rotor copper losses. Correct or not? Yes. Torque developed is equal to rotor copper losses divided by S by omega. The torque can be expressed in terms of rotor copper losses also. Rotor copper losses also. Indirectly is giving. In other words, damper winding only. Damper winding made with copper and the current in that it will cause copper losses. Here, losses are not important. Elimination of hunting is important. Correct? Losses are not important. And one question for you. When that rotor copper losses exist, tell me. Only during hunting condition only. During hunting condition only, the induction machine action is coming, then damper current. Okay. But how long hunting condition takes place? Transient period. It's not steady state. Steady state condition, no current in the damper winding, no copper losses. Nothing to worry. You damper winding. Okay. Yeah. This is one question. And another question also, see. Another question is like this. He has given a diagram. Okay. He has given you a diagram like this. And also rotor pole. This is south pole of the stator. And this is damper winding. But south pole of the stator is rotating at 1500 RPM. But rotor is rotating at 1490 RPM. Then damping torque developed by the rotor. This is F1. This is F2, F3, F4. The direction of force due to damper winding. Direction of force due to damper winding is A bit, F1, B bit, F2, C bit, F3, D bit, F4. That is your question. What is the answer? Tell me here. He has given you a small diagram. Then the direction of force due to damper winding, which direction? F1, F2, F3, F4. Okay. Which direction? What is your answer? Yeah. Yes. Answer is F2. Why? Because see here directly we can say don't apply right hand or left hand, all those things. Conclusions are there with you now. Believe it. Because when rotor speed has to increase, means what should be the torque direction? Definitely the damping torque must be in this direction. Then only rotor. Damping torque FD must be in this direction. Then only rotor speed increases. Na? Yes. Tangential force. You have to take tangential. This is the rotor. It has to torque must be counterclockwise direction. FD must be counterclockwise. Counterclockwise direction means F2. This is F2. Torque must be F2. If torque is clockwise, it is going to be F4. F1, F2, not like that. Rotor could not move up and downwards. Now it rotate. So here, rotor is here. It will move. Like this means tangential. You have to take F2 direction. Answer is F2. Okay. Yes. So torque must be tangential. You have to take always. Tangential is not curvature. No. This is the rotor. Means in this direction. It is rotating like this means what is the meaning of that? In this direction. Torque is in this direction. F2 direction. Okay. So these are the type of questions and the damper winding. Damper winding. Yeah. Now, yeah, before going to cylindrical machine, can you tell me any doubts are there on this? Please, some of you ask doubts. So we have completed total construction of salient pole alternator. It will take a lot of time, but cylindrical rotor, it won't take much time because we have established all our conclusions. We have gone through each and every reasonings. The cylindrical rotor alternator, we will complete quickly. Okay, but any doubts in this period, in this topic, tell me. This topic. So some of you are raising your hands now. Yes. Any doubts? Yeah. Any doubts? Unmute and you can ask. Raise your hands. Okay. Or you can chat box, you can write any doubt is there. No doubt is there, then we can. Some student ask a doubt. So won't damper winding increases the weight of the machine? Weight of the machine means actually salient pole machine is itself large length and size. Damper winding won't increase that much. Winding insulation, it won't increase that much weight. Correct? Weight increases also, we have to bear that. But running condition, under running condition, there is no inertia, nothing. Na? Even weight is more, running condition, no inertia. Because it is 500 megawatt alternator, say, definitely size is larger. The weight is not a matter. And one of the student asked, won't damper winding increases the weight? Definitely increases, but not how much by winding. Sir, have you left the EMF equation or EMF equation? I am going to do it. After construction, I will derive the EMF equation. EMF equation, flux linkages, rate of change of flux. We will come across. We will come across that. Is the synchronous machine is self-starting? Not, please explain. It is not, synchronous motor is not self-starting. Motor, generator, we will rotate. Synchronous motor only, not self-starting means the term valid for only for synchronous motor. Generator, I will rotate with the prime mover. And there is a question of not self-starting. Yeah, ourselves we will rotate. Okay. Yeah. Right. Any doubts? Some of you are raise your doubt. Hands, please ask.
Good morning, sir.
Good morning. Tell me.
Sir, during damping action, there is both current ID is flowing, so there is both generating and motoring action takes place in the damper winding.
Yes, yes. Motoring action takes place due to damper conductor. Just like induction motor is there, na? Torque is developed by stator flux and rotor current.
Rotor current.
Yes, rotor current.
And here in the diagram, you have shown only the how the torque TDL developed.
Yeah, torque is armature flux and damper current, ID.
Okay, okay.
Yes. Yeah, fine. Okay, anyhow, any doubts
Hello,
are
sir.
there? Yeah, who is there?
Ashish.
Ashish, tell me.
So actually, when these speeds NR and NS is same equal, then after that the damper winding action will over, sir. You get over.
Yes, yes. Again, when road changes, then it will come into picture. It is a transient nature. Transient. Whenever rotor speed changes, then only. It's very rare, na? Not only disturbance condition only it will comes into picture. During disturbance.
Sir, you have written your choice or choice losses of synchronous. Choice means, sir?
Choice, what is choice?
Sir, you have written choice of losses of voltage stability. Sir, that choice means
yeah. For example, generator, if you take generator. When rotor is too much oscillating, induced EMF, what will happen? Good point. Induced EMF frequency also changes. Na? Supply voltage, it is connected to the grid. V frequency fixed because armature winding is connected to the grid. But in the generated EMF, when speed changes, EMF frequency changes. When EMF frequency changes, what about the current? current V E minus V by ZS. But this frequency different, this frequency difference, right? And the delta angle between those two E and V, delta also continuously changes. Changes. If they exceeds beyond a particular value, loss of synchronism takes place. Circulating currents are very high, then definitely machine loses its synchronism. That is your point you wanted to ask, or any other point?
Related to that only, sir.
Yeah, definitely. When voltage fluctuations are more, induced EMF voltage fluctuations, generated EMF flux, induced EMF also keep on changes. Actually, what is the angle between E and V? Delta, na? Angle between delta. E. Of course, now I don't want to introduce the term delta. Now, if you introduce, you can't understand that at the time of after armature reaction, voltage drop, at that time we will see. Delta, na? Yes. For example, induced EMF and V both are same frequency, say, angle will be maintained same as long as load is same. But when load suddenly changes, say, E frequency changes. E frequency changes means angle between E and V keep on changes, na? Keep on changes. If delta more than 90 degrees, what is going to be happen? Angle changes because one vector is moving faster, one is slower, say, angle, it may be even more than 90 also. There is a choice of loss of synchronism.
Okay, sir.
Correct. If both phasors are rotating with same frequency, same speed, when both will rotate at same speed, both frequencies are equal. But induced EMF frequency changes when rotor speed changes, generated EMF frequency changes. Okay. Right. Yeah. Now, then let us go to the next topic. Yeah. Any doubts are there at the end? After the class, I will definitely, or I have given my phone number also, na? I have given my phone number 98 yesterday. Again, I am going to write. Any doubts are there? You please write. Give your queries. I will answer. So WhatsApp number is also same. Once again, I am writing my phone number 9849719672. WhatsApp number also same. Okay. You can note down. And at any doubt is there, please you can ask. I will answer. Immediately, if may not be immediately, if I have some work, say, definitely I will reply after some time. After some time. I used to give my number, which last time classes also you can find. I have given so many times and the people interacted. Because in the class, I cannot interact because hundreds of people are there. Na? I cannot answer all the questions because if all the questions are there, other people are simply seeing, again, the entire class is disconnected. So that's the reason I cannot attend all the, no problem. Whatever your question is there, you can please type text for the WhatsApp. Definitely I will answer. And if required, I will call to you people also. If I can't able to write clear with the chart, I can call you people and I will find out what is your exact doubts. I will answer. Okay, na? Yeah. Now, let us go to the next topic. Okay. Let us go to our next topic. That is cylindrical rotor synchronous machine. Cylindrical rotor synchronous machine. Cylindrical rotor alternator. Okay. Cylindrical rotor alternator. Cylindrical rotor alternator, it is circular shape. Rotor is circular shape and it will have slotted area and unslotted area also. Okay, let me draw. I want to see the good diagram. Oh. Okay. Not coming as a circle. It's circular shape. Okay. Cylindrical shape. I'm not happy with this diagram. Space problem. Yeah, this is better. Fine. Circle. On this rotor, what will happen? Unslotted area and unslotted area. There is some area slotted, some area unslotted. Unslotted. Slots are made on this periphery. Slots are made. This is slotted area. Yeah. Winding is kept in the slots. Slotted area. And there is no slots here, dear students. There is no slots in this portion. No slots. Okay. So these are the outer periphery is slotted. Outer periphery is slotted to accommodate the field winding. These are the slots made under the rotor. Outer periphery of the rotor. Slots means we will cut that portion. Slots is nothing but I want to keep the winding in the rotor. Definitely you have to remove that portion. You have to cut the rotor portion. And in that we need to keep the winding. Just like a rectangular portion we will cut. By cutting tools, by punching machines we will cut simply. Remove that portion. Remove that iron piece. In that you keep copper winding. Windings are made with copper, na? Yes. So in this we will keep the winding. Yeah. This is the winding. Field winding. Field winding we are keeping in the slots. Okay. On this side also, winding can be kept on this side also. For example, this is one. All the coils will be connected in series, no? This one coil. They are connected in series. Finally, we will bring two terminals outside. They are excited with DC. This is a cylindrical rotor. Cylindrical rotor. Taken? Yeah. Unslotted area, slot area. This is unslotted. There is no slots, dear students. There is no slots here. There is no slots here. But this is slotted area. I've taken 5 slots on this side, 5 slots. But this portion, there is no slots. Unslotted portion. Unslotted portion. Yeah. See, how many coils I have taken? 5 coils. 5 coils is coil sides are kept here, other coil sides are kept in the left side. Okay, yes. Listen. Yeah. Stop writing, stop writing. See, this is my rotor, cylindrical rotor. Cylindrical rotor. Okay. Here, there is no slots, dear students. There is no slots here, no slots here, no slots here. Only this portion is slotted, this portion is slotted. Okay. Yeah. And we are keeping the winding. We are keeping the winding. One coil side is kept here, other coil side is kept in the opposite slot. One coil, 1 dash say. And second coil is kept in the second slot. The winding is, so once on the diagram you can see one side of the coil sides, other coil side opposite side. No? This side you can see, say, this side opposite side. So how all the coils are connected? Listen. This is one coil. Other coil side is kept on the opposite slot, opposite slot. So first coil beginning is kept in the first slot, ending is kept in this other slot. And the second coil is kept in the second slot, ending is kept here. Third coil is kept here. And fourth coil, fifth coil. But end of the first coil, this is beginning, and end of the first coil is connected to beginning end of second coil, beginning end of second coil. End of second coil is connected to beginning of third coil. End of third coil, beginning of fourth coil. Fourth coil end, beginning of fifth coil. And this end will be taken outside, given with DC excitation. How all these coils are connected? Coils are connected in series. 1 dash, 2 dash, 3 dash, 6. All coils are connected in series. Finally, we are bringing two terminals outside to give the DC excitation. DC excitation. Why DC excitation? For the formation of the poles. Yeah. Now tell me, based on the current direction, this is the field current, no? Field current direction in this. This is the field current. Field current is entering here. When field current is entering, what is the direction of the current? Current is in this direction. Here current enter, current is in this. A cross here. Here they will form as a cross. But what about here? This is dot. Other side dot. Again current is coming. Current enter here. Cross. Here cross. Or right side cross. And the same current is leaving. Current is entering here. Current is leaving the other side. If your observer is here, say, he will feel cross, this side dot. This side dots. So here it is dot. Again current is coming. Again cross. Here cross. Current is entering. This is dot. Cross. This is dot. Cross. Dot. So finally current is leaving. So right side of the slots, all the current is entering. Crosses, no, they are crosses. They are crosses. Or let me with the red color. Crosses, all these are crosses. But this side, all they will be dots. Okay. All these are the dots. Now, based on the current direction, it's a core. Core is made with magnetic material. Then poles will form. You can find. To find the polarity of the pole, apply the thumb rule. See, here, crosses current is entering, current is leaving. Current is entering, leaving means it is giving the flux. So flux is coming outside, no? Yes. They are giving flux this side. These are flux are giving. When flux is giving means how it is act as. When it is giving the flux outside. Okay. When it is giving flux is outside means how this act as north pole. North pole will form here. This is act as a north pole. Unslotted portion is there, na? North pole. This side it will act as a south pole. This entire portion, unslotted portion, form as a north pole. This act as a south pole. And lengthwise, this is not only here, lengthwise all total, this total thing act as a north pole. And this is giving the flux upwards. This bottom portion is there, na? Bottom portion will act as a south pole. The entire bottom portion act as a south pole. This portion act as a south pole. Okay. The rotor, na? This is a rotor, say. The rotor. In this rotor, this is slotted area. This is a slotted area. This top portion is there. Na? This is acting as a north pole. This is a north pole. This bottom portion act as a south pole. Bottom portion act as a south pole. South pole. How many poles we have found? 2 poles. This is a 2-pole machine we have taken. 2-pole. 2-pole rotor. In this fixed area is slotted area, unslotted area is there. Na? Unslotted area form the poles. Where unslotted area, that will form a pole. But there is a fixed ratio, slotted area, unslotted area. 2/3 of the periphery is slotted, 1/3 is unslotted. 2/3 of the rotor periphery is slotted to accommodate the field winding. This is 2/3 of the periphery. 2/3 of the periphery is slotted. This side, this side. So for example, total 360 degrees say. Total 360 degrees means this is 120 plus 120. How much? 240 degrees. Slotted area. 240 out of 360. 240 out of 360 means 2/3. But this is 60. This is 60. Unslotted area 60, 60. 60 plus 60, 120 out of 360 degrees. And 1/3. 1/3 is unslotted. 2/3 is slotted area. That is fixed for any number of poles. Any number of poles. So let me write that point mainly. Okay. I just want to write the conclusions. 2/3 of the rotor periphery. 2/3. 2/3 means 240 degrees out of 360 degrees. Out of 360 degrees. 2/3 of rotor periphery. 2/3 of rotor periphery is slotted. Is slotted to accommodate the field winding. 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 And 1/3 is unslotted. 1/3. 1/3 means how much? 120 degrees total. 120 out of 360. 1/3 is unslotted or left. 1/3 is left or unslotted. 1/3 is not slotted. Unslotted. For the formation of the poles. For the formation of the poles. 1/3 is unslotted. For the formation of poles. Poles will form on the unslotted area. Unslotted area. Okay. Yeah. Unslotted area. Right. This is not only for 2-pole machine. I have drawn 2-pole machine earlier. For example, you want 4-pole machine. 4-pole machine means 4 slotted area, 4 unslotted area. 4 slotted area, 4 unslotted area. Only thing is rotor diameter will be more. 4 poles means rotor diameter is more. So for example, see, I would like to take 4-pole machine. This is the 4-pole machine means definitely rotor dia is larger. Rotor dia, but there are 4 slotted area, 4 unslotted area. See, these are the unslotted area. Here we can keep the winding. Winding can be kept like this. These are the slots. Okay, these are the slots. Slots can be made 1, 2, 3, and 4. So, how many slotted area? These are the unslotted area will form the poles. Unslotted area form the poles. Unslotted area form the poles. These are unslotted area. But in this, we will keep the windings, no? We'll keep the conductors here. Conductors. Winding can be kept here. Winding. Winding. For example, all these crosses. In this, it is crosses, say crosses. And these are the dots. For example, these are the crosses. Crosses. Here dots. Dots. Here crosses, in this conductors crosses, here dots. So between cross and dot, one pole will create, na? Here north pole will create, here south pole will create, north pole, south pole, south pole. This is 4-pole machine, 4-pole rotor, 4-pole rotor. Actually, lengthwise also it will be again like this, na? Lengthwise it is like this. This is forming one pole. This is forming one pole. This top one is one pole. Of course, we are given it is slotted area. Slotted area. And this is again slotted area. Where unslotted area is there, na, poles will form. Unslotted area. This entire thing acts as a south pole. This is south pole, south pole. This is north pole. And again, this is south pole. This is the north pole, north pole. 4-pole machine, 4-pole machine. And in that, angles will be, how much angles? See, this is the 30 degrees, slotted area 60, and this is also 60 degrees. This is also 60, this is also 60. Therefore, what is the slotted area? Slotted area. Slotted area is 60 plus 60. How much total? 60 into 4. That is 240 degrees, na? 240 out of 360. Slotted area total 240 degrees. All 460 is 240 degrees out of 360. That is how much? 2/3. 2/3. But unslotted area is 30. This will be 30. This will be 30 degrees. This will be 30 degrees. 30. How much? 430s. 430s means 120. 430s means 120 by 360. 1/3. 1/3. Okay. Yes. Slotted area 60 plus 60 plus 60. 60 plus 60 plus 60 plus 60. Total is 240, na? Yes, that's what. This is a slotted area. Similarly, unslotted area 30, 30, 30. This is fixed. How many number of poles are there? That is fixed. Slotted area, unslotted area. Okay? Right. Okay. Right. Fine. This is clear, na? Yes. 360 degrees. 240 out of 360. 2/3, 1/3. 4-pole rotor. And there is also the shaft will be there. Shaft. How shaft? Rotor shaft also. This is a rotor shaft. No? Yes. Actually, rotor will be like this. Rotor shaft. Okay. Yeah, some of you have given, you can use circle tools, but the sketchboard is not downloaded in my system. The sketchboard is not downloaded. That is what I am trying actually. So I am writing on whiteboard. Okay, I will try. And there, yes, we can use directly circles and straight lines, whatever it is there. Options will be available. Okay, I will try to download it. So there is some problem. It is not downloading actually. Okay. Now, lastly, yeah, just after 5 minutes, we'll go for a break. This is the rotor, na? Yeah, rotor. This is cylindrical rotor. Now, if you add stator on this, stator will be anyhow, it is a circular shape. This is the stator. Stator. Stator is same. Whatever the stator we have seen in cylindrical machine, here also stator is same. Stator will be same. Okay. Stator circular shape. Stator is circular shape. And this is said to be direct axis or polar axis. This is D axis. D axis. And this is the Q axis. Q axis. Q axis. That is D axis. Here, both are circle. Na? Stator is circular shape, rotor is also circular shape. When both are circular shape, air gap is uniform. Air gap is the same. Air gap is same along the direct axis and also quadrature axis. Both are circle. Important thing is air gap is uniform. Air gap is uniform. Flux distribution is sinusoidal. Air gap is uniform. Air gap is uniform. When air gap is uniform, flux distribution also sinusoidal. Flux distribution is sinusoidal. Flux distribution is sinusoidal. Yeah. But how it is sinusoidal? Flux distribution is sinusoidal. Dear student, how flux distribution is sinusoidal? See, when we are keeping rotor, na? When we are keeping rotor, unslotted area, slotted area. So here I have taken 5 slots, 1, 2, 3, 4. Slotted area, we are keeping winding here, na? Winding we are keeping like this. Winding we are keeping. For example, if you take, this is 1, 1 dash, 2, 2 dash, 3, 3 dash, 3, 3 dash. Due to each 1, 1 dash, MMF will be a rectangular wave. Rectangular. What I mean to say is, flux is equal to MMF by reluctance. Na? Flux is equal to MMF by reluctance. That reluctance is proportional to air gap. Air gap. In salient pole machine, what we have done? In salient pole machine, by chamfering the salient pole, we can able to get flux distribution as sine wave. Flux distribution sine wave. Salient pole machine. Why? Because reluctance we are changing. Reluctance is minimum at the center of the pole, increasing towards the pole ends. Increasing towards the pole ends. But whereas in cylindrical machine, how it would be? In cylindrical machine, if stator is circular, say, and rotor also circular. Rotor also circular. If you keep only one slot means how waveform? Flux distribution. Flux distribution will be, for example, it is 1 and 1 dash. If you take 1 and 1 dash, 1, 1 dash, it will be flat topped wave exactly. And flux is equal to MMF by reluctance, na? MMF by reluctance. But MMF is constant. DC excitation we are giving. DC excitation we are giving. So when DC excitation means MMF is constant, air gap also constant. Cylindrical rotor, air gap is constant. Then what is the MMF? MMF constant, reluctance constant means flux distribution also constant. This is the type of flux distribution. V wave you will get with the coil 1, 1 dash. With 1, 1 dash you will get like this. Okay. But there are many coils are there, na? Like 2, 2 dash, 3, 3 dash. How you are going to get for that? Okay. Here North Pole, South Pole. How you will get means, so each coil, due to each coil, they will be like this. So for example, I will take north pole side. North pole side. Yeah. North pole side. The MMF waveform due to one coil, it is like this, 1 1 dash. But 2 2 dash, its space is less. 2 2 dash is like this. 2 and 2 dash, the coil distance is less, space is less. Like 3 3 dash, it is still less. Area is less. Area. 1 to 1 dash means it will produce MMF rectangular wave. 2 to 2 less. 3 3. 3 and 3. Due to this, you are going to get resultant waveform as a sinusoidal. All MMs are aiding, na? So resultant waveform you will get almost as a sinusoidal. Almost as a sinusoidal. Strictly speaking, it will be stepped waveform. Strictly speaking, actual waveform you are going to get like this. Stepped waveform. It is a stepped waveform. Stepped waveform. This is actual waveform. That is almost as a sinusoidal, no? Almost as a sinusoidal. The flux distribution can be obtained sinusoidal by distributing the field winding. We are not keeping only in one slot. We are keeping in one second slot, third slot, but area of third is less. Space is less. Their MMF also less. Like that, all MMFs are aiding so that they will produce the net flux will be sinusoidal. The flux distribution. The flux distribution you will get almost as a sinusoidal. Okay? Yeah. So your conclusion is, important point is, in cylindrical rotor synchronous machine. Yeah, we'll go for a break, just 2 minutes. After this, I will stop and we'll go for a break. In cylindrical rotor synchronous machine, the flux distribution can be made. Flux distribution can be made sinusoidal. Can be made sinusoidal by distributing the field winding. By distributing the field winding. By distributing the field winding in more number of slots. Distributing the field winding in 2/3 of periphery. Distributing the field winding in more slots. In more slots. That is 2/3 of the periphery. 2/3 of rotor periphery. 2/3 of rotor periphery. Okay? And by distributing more slots, more sinusoidal. More sinusoidal. But practically 2/3 is enough. 2/3, because slotted area also must be required. Unslotted area also must be required. Unslotted area also must be required. Yeah. That is your question. Cylindrical machine, salient pole machine, chamfering. Cylindrical machine distributing the field winding. Okay. Without distribution, what is going to be happen? Just a minute. Stop writing. You may be thinking, sir, I will create big slot. I will keep all conductors only in one slot. If you keep, see, dear student, what I want to explain. Stop writing. Just a minute. Look, I am discussing about this diagram. Why to go more number of slots? Only one slot. I will keep all winding only in one slot means 1 1 dash also like this. If you keep second coil also there, 2 2 dash also like this, 3 3 dash also like this, 4 4 dash also, all they will be. Then how resultant is going to be? Resultant you will get all they will be added up. Like this you will get resultant. Resultant you will get only flat top. Correct? Because all coils are kept in same space means the space is same. Entering, leaving. During that period, it will produce, every coil will produce rectangular, but same size. Same size means, so you will get rectangular waveform. That's the reason I am keeping coil 1 here, 2 here, 3 here. So their MMFs also, their width is less now. Overall, finally they will produce. But all MMFs are aiding. Cross dot, all they are aiding. So you will get flux distribution by distributing the winding. Okay. Yeah. Right. So let us go for a break. And after that, I will continue this. We will continue this cylindrical rotor alternator, but it is going to be larger length, smaller diameter. Right? Yeah. Shall we go for a break or let us continue? Just tell me. Or it may take another some 20 minutes or 15 to 20 minutes to complete this. Break may be better. Yeah. Otherwise, it is 30 minutes break. Take the break for half an hour and then we will continue. But it won't take much time. No problem. If you take break, our minds will be fresher. Then still we will complete quickly that construction of alternator. Otherwise, it's already saturated, and then our minds may not accept. Okay. Take the break for 30 minutes. Break for 30 minutes and then come. Now it is around 9:06. Break for 30 minutes. Now class will start at 9:36. Okay, 9:36. Okay. Now, what is the doubt? Some of you have raised your hands. Tell me. Hello. Hello. Yeah. Okay. Let us go for a break and then we will meet. Yeah. So fine. Came back. Are you ready? Okay. Yeah. Just I'm giving some cushion time, 1 or 2 minutes. Okay. So anyhow, construction it will take a bit time, no doubt. But once this construction is completed, any examination that must be there in your notebook. That is my intention. So after completion of construction, you can verify any examination question. Answer will be there in your notebook. That's all. Because you cannot read 10 textbooks in yes. All information will be readily available and in understandable way, so that you can remember in your mind. Because you can't read some 10 textbooks. We can read 10 textbooks because we are handling only one machine. I am not going to write examination. You need to write examination. Yes, time is limitation is there for you. To read so many subjects, it's not that easy. So if ready-made information is available with understanding way, it is easy. Okay. Okay, right. Now coming to the, so flux distribution can be made sinusoidal by distributing the field winding. Field winding is distributed in more number of slots, 2/3 of the periphery. Purposely it is 2/3. Why? Because more sinusoidal. More sinusoidal. More steps you will get. More slots. Here I have taken 5 slots, say 5 steps. Instead of that, if you take more slots, more steps. This is north pole side. South pole side, it will be negative half cycle. South pole side, it is going to be negative side. Negative half cycle. This also like this. Negative half cycle. Negative half cycle. This is under north pole. This is under south pole. Flux distribution will be. Okay. Now coming to the other points, let us discuss. Yeah. Coming to the cylindrical rotor. See. Cylindrical rotor. Rotor is made with solid steel. Rotor is made with solid steel. Forging of nickel, chromium, and molybdenum. The meaning is rotor is made with solid steel. It is not laminated. Solid steel, forging of nickel, chromium and molybdenum. To increase the mechanical strength. To increase the mechanical strength. To increase the mechanical strength. Made with solid steel, forging of nickel, chromium, and molybdenum to increase the mechanical strength. It is solid steel, not laminated. Rotor is solid steel, solid bar. Okay. The rotor is, this rotor is there, na? Rotor is a solid piece, solid bar, circular shape, solid bar, not laminated. Outer periphery is slotted, in that winding we will keep. Right? Yeah. So, made with solid steel, forging. Forging means what? Forging means alloying with nickel, chromium, and molybdenum to increase the mechanical strength. The steel mixed with these material, nickel, chromium, and molybdenum. Forging is the process of heating. Forging means heating and hammering. By adding all these things, steel, it will be heated few hundreds of degrees centigrade and it will be pressed on all 360 degrees. The rotor will be pressed. This is the rotor say. By mixing, it is pressed with the machines. Correct? Yes. So therefore, by hammering, in other words, some kind of hammering or pressing in all 360 degrees, rotor becomes mechanically very strong. The process is called forging. Forging is nothing but heating and pressing, heating or hammering. So with the heating and hammering, strength is more strength, mechanical strength, to increase the mechanical strength. Okay. Now coming to rotor is mechanically strong, balanced well, because it is circular shape. It is simply circular shape, is mechanically balanced well and also more strong, less air friction, air gap is uniform. Air friction is more in salient pole machine. Cylindrical, less air friction, less hunting, also less. Hunting is less. Why? Because salient poles are in earlier generator, salient pole machine poles are projected type, pole 1, pole 2, pole 3. They are coming out from the rotor periphery. But is a cylindrical rotor, poles are coming outside of the periphery? No. A part of the rotor is itself act as a surface, unslotted area act as a pole. So rotor is balanced well. Hunting is also less. Rotor oscillations are less. So rotor is mechanically strong, balanced well, less air friction, less hunting, less centrifugal forces. So these type of rotors can be driven at high speeds. High speed you can rotate. That's the reason these are called high speed alternators. High speed alternators. Let me add that point. Yeah, cylindrical rotor is mechanically balanced well. Cylindrical rotor is mechanically balanced well. Cylindrical rotor is mechanically balanced well. Mechanically balanced well. Come strong. Forging, mechanically balanced well, strong, and less centrifugal forces. Less centrifugal forces. Come on, less air friction. Air friction also less, na? Yes, less air friction. And less hunting. Less hunting. Hunting is less hunting. So these rotors can be, therefore, these rotors can be driven. These rotors can be driven at high speeds. Can be driven at high speed. High speeds. That's the reason called high speed alternators. That's the reason called high speed alternators. High speed alternators or turbo alternators. Turbo alternators. Turbo alternator. Turbo machine. Turbo means high speed. Turbo means high speed, large size of the machines are called turbo machines. High speed, large size, turbo machine. So these are high speed alternators. High speed alternators. Right? Yeah. The speed range is speed range. So speed range is 1500 RPM to 3000 RPM. 1500 to 3000 RPM. 15 to 3000 RPM. High speed. Now for 50 Hz frequency, or F is equal to 50 Hz frequency, what is the number of poles? Number of poles. Number of poles. Yeah. This is speed range 15 to 3000 RPM for frequency 50 Hz. For frequency, F is equal to 50 Hz, minimum 15, maximum 3000. And it will be 1800 RPM to 3600 RPM for frequency 60 Hz. For frequency 60 Hz. Okay, yes. Minimum 15, maximum 3000 RPM. For 60 Hz, 18 to 3000 RPM. High speed, 3000. Whereas in hydroelectric power station, 300. No? Salient pole machine 300 RPM. Here 3000, 10 times. Cylindrical machine speed is 10 times maximum, high speed alternator. Then what is the number of poles? See, number of poles. Number of poles are 3000 means 2 poles, 1500 RPM. It will be 4 poles. Number of poles either 2 or 4. Number of poles are minimum 2, maximum 4. 3000 is 2, 1500 4. Minimum 2, maximum 4. Not more than 4. More than 4 means now salient pole machine. Salient. Cylindrical machine only minimum poles are 2, maximum 4. Maximum 4. Okay. Yeah. But among these 2 poles are preferred. 2 poles are preferred. Why 2 poles are preferred? Already I have given the very beginning class. 2 poles, because with 2 poles 3000 RPM, high speed steam power stations. These alternates we are going to use in steam power stations, right? So efficiency is good. Its efficiency will be good. Efficiency will be good. The 2 poles are preferred mostly. Worst case 4 poles. Okay. But when you are using 2 poles, I am also going to show the diagrams also, practical physical pictures, how salient pole cylindrical. I am having that. After completion of this, I am going to present that physical pictures of the alternators also we are going to see. First, let me complete. So 2 poles, minimum poles are there now. When minimum poles means rotor diameter is smaller. Diameter is smaller. Rotor dia is smaller. Since minimum number of poles, therefore smaller the diameter, smaller dia of rotor. Smaller dia of rotor. But diameter is smaller, length must be larger, no? For a given power, length must be larger. Power is proportional to D square M. D square M. So they will have smaller diameter, larger axial length. Larger axial length is larger axial length for a given power. For a given power or rating. For a given power or rating. For a given power, fixed power, constant power. If you compare cylindrical and salient pole machine, it will have smaller diameter for the same power rating, but length is larger length. Its diameter is, length is nearly 5 times that of the diameter. Length is 5 to 7 times that of the diameter. 5 to 7 times that of the diameter. L by D ratio, larger length, 5 to 7 times that of the diameter. L by D ratio, 5 to 7. Larger length, smaller diameter. Next, coming to what type of prime movers are suitable? Prime movers. Suitable prime movers. Suitable prime movers, that is turbines. Turbines. Suitable turbines are steam turbines. Steam turbines are suitable. Steam turbines and gas turbines. Steam turbines are designed for high speed. Steam turbines are designed for high speed. Steam turbines and gas turbines. And gas turbines. Steam turbines and gas turbines. Steam and gas. Can you tell me why steam turbines are designed for high speed? Why hydro turbines are designed for low speed? Hydro turbines are for low speed, steam turbines for high speed. Because steam pressure can be increased like anything. Steam pressure, if you hundreds of degrees centigrade, even 1000 also, 600, 700 degrees centigrade, or even 1000 degrees centigrade. At high temperature, steam pressure is high. Pressure can be increased like anything. Therefore, steam can hit the rotor to rotate few thousands of RPM, 3000, 3600 RPM. Steam can drive, but water cannot. Even water, we cannot heat nothing. Na? Okay. So only water, it is depends on the head available, how much head height is available. So water cannot drive that much speed. Water turbines are designed only for few hundreds of RPM, 200, 300, 350 RPM, that much only. But steam turbine, thousands of RPM, high speed. Steam pressure can be high. Okay. Suitable turbines are steam turbines and gas turbines. Therefore, cylindrical rotor alternates are suitable for steam power stations. Cylindrical rotor alternator. Cylindrical rotor alternators are suitable for steam power stations. Steam power stations means thermal and nuclear. Thermal and nuclear power stations. Thermal power station, nuclear, steam power stations, and gas power stations. Gas power stations. Steam and gas. Okay. Yeah. These are suitable for steam power stations. Fine. Now lastly, damper winding. No damper winding exists in cylindrical machine. Why no damper winding? Hunting will be there or not? Yes, hunting takes place in synchronous machine. It may be cylindrical or salient pole machine. Hunting takes place, but that hunting is less. Hunting is less pronounced in cylindrical machine. Salient pole machine hunting is more. Why? Because salient poles are projecting nature. North pole, south pole, they are projecting outside. So air gap is more and projecting nature. Oscillations are more, but here oscillations are less. Hunting is less. Hunting will be there, but hunting is less pronounced. But though that hunting can be eliminated with the solid steel rotor. Solid steel rotor is itself act as a damper bar. Earlier we have taken, this is made with solid steel. Now purposely we are making with solid steel. Okay, this is solid steel. Why solid steel? Mainly to eliminate the hunting only. The solid steel rotor is itself act as a damper bar because it is having large length, smaller diameter. So that is itself act as a iron bar, steel bar. Steel is also conducting material. Na? Yes, steel also conducting material. Eddy currents are induced in the rotor core. That eddy currents will eliminate the hunting. Eddy current damping. It can be called eddy current damping. Eddy current damping. It's like, first let me write, no damper winding exists. No damper winding exists in cylindrical rotor machine. No damper winding exists. No damper winding. Not required. Exist in cylindrical rotor synchronous machine. Cylindrical rotor synchronous machine. Because hunting is less pronounced. Hunting is less pronounced. Hunting is less. Hunting is less pronounced. Though the hunting can be eliminated, hunting can be eliminated with eddy current damping. With eddy current damping. Eddy current damping. Eddy current damping means rotor. Iron core, na? Yes. The rotor is You have taken this now, I'm shifting the page. Though the hunting can be eliminated with eddy current damping. The solid steel rotor, the solid steel rotor itself behaves as a good damper bar. Solid steel rotor itself acts as a good damper bar. But when rotor speed is less than or more than synchronous speed, eddy currents are induced in the damper winding. Eddy currents are induced. That eddy currents interact with armature flux will develop the damping torque. The solid steel rotor. See here, this is the stator core, no? This is the rotor core, say. This is the rotor. Rotor core. Okay. And when stator poles are there, for example, if you take stator poles, these are the stator poles. Stator. Fine. On the stator, poles are rotating. And the stator, poles will form, na? Yes. For example, say this is north pole of the stator or south pole of the stator, say. This is south pole of the stator. And this is north pole of the stator. Here also poles will form like this. On the stator, poles will form, na? Yes. RMF. Stator poles will form like this. This is a stator pole. And here, north pole of the stator. Rotating magnetic poles. North pole of the stator. How flux is coming? Flux is from north to south. They will take a path. This is the flux path. North to south, say. North to south. Flux will take return path. Flux will take return path like this, north to south. Okay, yes. And during this, when these poles are rotating at synchronous speed, the stator poles are rotating at what speed? Synchronous speed, say. It is rotating at 1500 RPM. If rotor is rotating some 1400 RPM. Rotor speed 1400 RPM. These poles will cut the flux. Say when rotor is 1400 RPM, what will be the current in this? Currents are induced here. This portion will cut the flux. This portion will cut the flux. The portion which is existing under the pole, they will cut the flux. What is the current in that? Okay. When rotor is slow, flux direction, conductor, motion of the conductor, left side we have to assume. What will be the current in this cross? And this is dot, cross and dot. So, whatever the portion it is there, we are not keeping any conductor. Dear students, we are not keeping any damper conductor. See, they will take a path like this, just like that. They will take a path like this. These are the damper current. This is damper current, eddy current. I can say eddy current. The portion which is existing under the pole that acts as a damper bar. You are not keeping any conductor. The portion which is existing under the south pole, it cut the flux. EMF is induced in this rotor body. Okay, lengthwise, south pole is like this. So this acts as the piece which is existing exactly there, act as a conductor. So current flow takes place. Eddy current. And these eddy currents interact. Now, damping torque is proportional to what? Armature flux and damper current, ID. So that is nothing but eddy current. This is itself what I am saying, eddy current damping, eddy current torque. So no damper bar is required because hunting is less. That's the reason we are using solid steel. Solid steel rotor we are not making as a lamination. If you do lamination, what will happen? Tell me. If you laminate this, what is going to happen? If you laminate, then eddy currents are reduced. No? If you laminate, eddy currents will reduce. Eddy currents are going to be reduced. But we want eddy current. When eddy current is more, then only hunting is effective. That's the reason it is not laminated. It's not laminated. Purposely, we don't want any lamination because I want more eddy currents so that more torque. Eddy current losses will be there, okay. And some of the students will raise it out. Sir, eddy currents continuously takes place. Not continuously. When eddy currents takes place? Eddy currents takes place only during hunting only eddy currents will comes into picture. Why? Because EMF is induced only when rotor deviate from synchronous speed. Steady state condition, no eddy current. Because steady state condition, relative speed between the rotor, core and armature flux. Relative speed between armature core and rotor, relative speed is 0. When relative speed is 0 means no induced EMF, no flux cutting, no eddy currents. And that to be, is there any eddy currents due to DC current? Of course, in the field winding, we kept on the rotor. I am not showing that field winding, but in the field winding, they carry the DC currents. DC currents. Due to that, there is no eddy currents. DC winding, there is no eddy currents. But when eddy currents will comes into picture, only when rotor deviate at synchronous speed. Synchronous speed, eddy currents will come. That we want it. Then the last important thing is damping torque is required. So the currents will induce only when the rotor oscillate during hunting only. So if there is no hunting, no eddy currents. Okay. Yeah. It is not, lamination is not required. Lamination is not required because they are carrying the DC currents. Na? Field winding, main winding is field winding, DC. They do not produce any iron losses. That's the reason no need of any laminations. Okay. So therefore, the conclusion is statement is the solid rotor is itself act as a damper bar. Na? Yes. When rotor deviate from synchronous speed, when rotor rotate other than synchronous speed, or rotor deviate from synchronous speed, when rotor deviate from synchronous speed, the solid steel rotor cuts the armature flux, stator flux, cut the armature flux, that is stator flux, and EMF is induced. This induced EMF will maintain eddy currents. This induced EMF will maintain eddy currents. Eddy currents in the rotor body. Eddy currents in the rotor body. These eddy currents interact. These eddy currents interact with armature flux. Develop required damping torque. Develop required damping torque. Develop required damping torque. Okay. Now, develop required damping torque. Yes. Yeah. So this is about a cylindrical machine. So I have given one question, a previous gate question. In a salient pole machine, hunting is eliminated by rotor copper losses. But now can I say it is rotor iron losses? Yes. Eddy current losses, rotor. These are also rotor losses, but iron losses. These are iron losses. Cylindrical rotor synchronous machine, hunting is eliminated. For example, I want to prepare a question. In cylindrical rotor synchronous machine. In cylindrical rotor synchronous machine. Cylindrical rotor synchronous machine, hunting can be eliminated. Hunting can be eliminated with a bit by a bit. Stator copper losses. Stator copper losses, B bit. Rotor copper losses, C bit. Rotor iron losses, and D bit. Stator iron losses. Stator iron losses. Stator iron losses. What would be your answer? Your answer will be stator iron losses. Will be stator iron losses. Stator iron losses. The eddy current losses, in other words, eddy current losses. Eddy current losses are iron losses, na? These are itself eddy current losses. Eddy current losses. Yeah, fine. Okay. So with this, construction is completed. Yeah, now I just want to show some pics related to this construction. Let us see. Are you ready? Okay. I'm sharing the slides. Okay. Dear students, see here. Who is this person? Who is this? Faraday. Okay. He is the Faraday. See how stylish Faraday is. Your godfather. He invented that alternators, no? Yes. He's experimented and shown that results. Alternator works on the principle. The Faraday. Okay. And who is this? Can you tell me who is this? Do you have idea? His name is. For example, in interviews, if I want to ask very tough questions, say, who is this? Very good. Lenz. Oh, great. He's a Lenzer. His name is Lenz. Good. Lenz. Lenz law. He has given the Lenz law. He's a Faraday and Lenz law. Right? Yes. Okay. Just I have taken for this. Sorry. I think it is not there. Okay. When coil is going, you can find it is not a big. I don't know. There may be some problem. We need to upgrade the media object. Okay. This we will see anyhow. Why? Waste of time. Coming to see, this is the stator, dear students. This is the stator core. The stator. See. These are the stator core is laminated. Is a stator core. Stator core. Can you find laminations? Stator core is laminated. Stator core laminations. This is one lamination. This is another lamination. Laminations. Stator will be laminated. And in that winding is kept armature winding. This is the armature conductors. All these are the armature conductors. Armature winding, stator winding. See how many slots are there? Very large, very large. Hundreds of slots exist in a practical machine. Hundreds of slots. There's armature winding. No, armature conductors. This is a stator. Stator core. Okay. Now, see this stator core. The stator core, you can find how these slots are there na? In the stator slots. These are the stator slots. All these are the stator slots. Stator slots. Slots. All these are the slots. In this winding is going to be kept. Armature winding can be kept in the slots. Okay. Now we can also see this is also stator, stator of alternator. Stator of alternator. Right? Even this is the winding now. These are the windings. These are the windings. Of course, outside, actually it can be kept in the rotor slots. You can find exactly here, stator of synchronous machine. Yeah. See conductors, all these are the conductors, no? These are the conductors. But they are kept in this. They are kept in the slots. These are the slots. Armature winding is kept here. Armature windings are kept in the slots. The slots. Armature winding. Okay. There are the thick plates. The conductors are not small wires. Thick plates they will be. Armature winding. Okay. This is the stator. I have shown a projection of the stator. Now coming to salient pole rotor is like this. See, this is the salient pole rotor. Salient poles. This is projecting nature, na? Salient poles. Poles are fixed to the periphery. Rotor. This is rotor shaft, na? This is a rotor shaft, and poles are the rotor shaft. Poles are fixed like that. I think, can you able to see the winding? This is the field winding. Field winding. Field winding. Salient pole. On that winding has kept salient pole. This is a 10-pole rotor. 10-pole rotor. 10-pole rotor. Salient pole rotor. This is also salient pole rotor. Can you able to see? This is salient pole rotor. Salient poles. These are the salient poles. Salient poles. Salient poles. And these are end connections, end rings. See, these are end rings. End rings. End rings are kept on the rotor on two sides. Two sides. What for end rings? To provide the path. Just like spiral cage induction motor endings are there. Na? Here also same function. They will complete the path. Where is the damper conductors? This is the damper winding, damper conductors. Can you able to see damper conductors? Damper bars are there, na? Damper bars. Damper bars. The damper bars are, but where the damper bars are kept? Slots made under the pole shoes. Salient pole alternator. Okay. This is the rotor shaft. See how shaft is there. This is the shaft. Shaft. To that, prime mover will be fixed. Prime mover will be fixed. Okay. Still, if you want to see clearly, see here. I have given damper bars. Can you able to see damper bars? You see damper bars. These are the damper bars. Damper bars. Damper bars. They are kept where? They are kept pole shoe, under pole shoe. But this is the field winding. No? Field winding is kept here. This is the field winding. Field winding with the copper wire. You can find it's a copper wire. No? Yes. Copper wire. Field winding. Yeah. This is about cylindrical, a salient. Now I just want to show the cylindrical rotor. How cylindrical rotor? This is the cylindrical rotor. Here students, see cylindrical rotor. How cylindrical rotor? Larger length. Length is very large. Diameter is smaller. Diameter is smaller. These are the slotted area. Slotted area. This is the slotted area. This entire thing is slotted area. Slotted area. But this portion is there, na? No slots. Unslotted area. Unslotted. This portion is said to be this and this unslotted. There is no slots, na? Yes. No slots. This portion, no slots here. Here only pole will form. This is itself act as a north pole, say. This portion is itself act as a pole, north pole, unslotted area. In that winding can be kept. Field winding. Field winding is distributed in the slots. Field winding. This is without a winding, without keeping winding, but I would like to show with after keeping the field winding, cylindrical rotor. Cylindrical rotor after keeping the field winding, how it is? Are you getting? Field winding is distributed. But this is unslotted area. This one is unslotted area. This is slotted area. Entire thing. This is slotted area. This is unslotted. There is no slots here. Unslotted area. Sorry. Okay, na? Here poles are going to be formed. For example, north pole means north pole will form here. This entire thing acts as a north pole. No slots here. Unslotted area. This is coil 1. I have shown 1, 1 dash, 2, 2 dash, 3, 4, 5, 6, 7 coils that are kept. 7 coils. 7 coils. How coils are kept like this? Cylindrical rotor. Okay. This is a cylindrical rotor. See field poles. How field poles? These are forming as the poles. These are the poles. Say this is north pole. North pole. Outside that's opposite side south pole. North pole and south pole. Field poles. This is the field winding. So is it projecting nature? Poles are, is it coming out? No. Same surface, a part of the surface of the rotor acting as a poles. Acting as a poles. Okay. Cylindrical rotor. This act as a pole. Is a pole. North pole. North pole. Similarly, yeah, you can find how rotor is going to be inserted. The rotor is ready to insert in the stator. Rotor is ready to keep inside of the rotor. Now you can find almost it is half of the rotor is inserted. half of the cylindrical rotor is inserted. But you check the man who is operating, his size and rotor size, very large alternators. The alternators, it may be 500 kVA, 500 MVA, large rating of alternators. Huge size. They will be inserted with the machinery. The rotor is not just kept like that. Machinery. Okay? Yeah. And this is, for the rotor, there are different types of excitation methods. Excitation. There are brushless excitation, the permanent magnet. This we will see later. Now you cannot understand what is total thing. You have not concentrated how excitation is given. From the beginning, I am showing only excitation with the DC battery. Okay, we will come this point later. Okay. Yeah. Right. These are the salient poles. Na? See, salient pole rotor is laminated, dear students. This is the salient pole rotor will be laminated, but cylindrical is not laminated. Cylindrical purposely it is not laminated, whereas salient pole rotor alternators are laminated. Laminated steel. This is a salient pole rotor, but cylindrical purposely it is not laminated, because there we want more eddy currents. Whereas in this damper winding is there, no? Damper winding is there. That will take care. That will take care. Okay. Yeah, this is about construction of alternators. Yeah. Right. In our diagram, this is our cylindrical rotor alternator. Na? Cylindrical rotor alternator. Okay, fine. But how excitation will be given? Excitation will be given from the beginning onwards. I am showing only excitation will be given as with DC battery, but it is not like that. There are three types of excitation methods are there. Excitation methods. You can refer in the material whatever I have given. I am not going to explain all three excitation methods. Examination point of view, they are not important. You never ask on the excitation methods. It is only matter of interest. That's the reason I have given in the material. Right? There are three methods. Excitation methods, how they are? Three methods are there. Excitation methods. Excitation methods. One is by using DC generator. One is by using DC generators. Second one is static excitation. Static excitation. Third one is brushless excitation. Brushless excitation. Three methods are available. Okay. You just to go through in the material. I have given very clear explanation. By seeing that diagram, you can able to understand. You can able to understand. So I just want to show how excitation, for example, see, this is by using DC excitation. By using DC exciter, how we can keep, yeah. Listen, this winding is there now. Winding I have kept with a battery. Actually, it is not like that, no? It is not just like that. There will be, yeah, there will be shaft. The shaft will be fixed to this. This is the shaft, rotor shaft. Rotor shaft. To this rotor shaft, shaft also extended on this side. Na? This side also it is extended. Is a rotor shaft. One side prime mover is connected. See, for example, this side prime mover is connected. Other side exciter. Exciter is a DC shunt generator. DC shunt generator can be used as an exciter. Shunt generator. These are the slip rings. Then you have brushes that will consist. Yeah. This is a exciter, is a DC shunt generator. Exciter is a DC shunt generator. This is a prime mover. Prime mover is mechanically coupled, and this generator also mechanically coupled. Exciter also mechanically coupled. Mechanically coupled. For this, how these terminals will be given? How this connection will be given? This connection is going to be like this. See, these are there now. Positive terminal. This is beginning now. This is beginning. How I can connect? This is positive brush. This is negative brush. No slip rings. With that, what we will do is simply I will bring like this. I will bring like this. It is connected to the positive terminal. Positive terminal end. And this end will be connected to the negative. This end is going to be connected to the negative. Negative. This is positive. Positive. Okay. Like if you rotate the rotor, you know, this is when we are rotating the rotor. If you rotate the rotor with the prime mover, then this also will rotate now. This also will rotate. Everything will rotate. Rotor rotate and shunt generator also rotate. Shunt generator act as an exciter. Shunt generator is a self-excited generator. No? For that, no excitation is required. It is simply self-excited generator. So when self-excited generator means due to residual magnetism, it will build up its voltage. You know the condition for build up of voltage. There is a residual magnetism. When it is driven, it will induce EMF, and that same residual magnetism will given the current to that. Okay. For DC shunt generator is a self-excited generator. You may be knowing there is various conditions. Condition for build up of voltage, there will be residual magnetism in the field poles, field terminals properly connected. I don't want to explain all those things. I can say only is a self-excited generator. And no separate excitation is not required. No separate voltage source is required. The armature is itself will given its field current. The armature current only giving the field current to this. And most of the current is giving to its load. Most of the current will be is coming like this. No? Yes. Some current is coming to here. This current will come because this is plus and minus a generated EMF. It is coming like this, and going through the positive slip ring, and entering here, entering cross, and again coming here, leaving here, and again coming like this, entering here, again coming, entering here, okay, and again coming, entering here, current, entering here. Finally, it will lose. It will come to here, taking the closed path. So DC shunt generator can be used as a voltage source. DC shunt generator can be used as a voltage source. Correct or not? Yes. Because DC shunt generator, what is the voltage characteristics? VI characteristics? V and I is almost constant. Whereas series generator rising characteristics. Series generator is rising. How series generator characteristics, voltage characteristics is like this, na? Voltage and current characteristics, rising characteristics. This cannot be used as a voltage source. No, this can be used as a voltage source. Shunt generator. This is for series generator. That is also a question for you. Which of the following DC generator can be used as a voltage source? Which of the following DC generator can be used as an exciter for synchronous machine? That will be shunt generator. Shunt generator can be used as a voltage source. Okay? Yeah. So when it is driven, I am coming to the operation. When prime mover is driven, like this now, when prime mover is driven, this rotor rotate, shunt generator also rotate. It is generating the voltage, and that generated voltage is a constant voltage, DC voltage, that will be given to the field winding, current circulating the field winding, then rotor poles are formed. Rotor poles are formed. Since rotor poles are already rotating, they will cut the armature flux. No? Yes, they will cut the armature flux. These are the armature slots. Armature slots. Armature slots. Armature conductors. Armature conductors. So they are cutting the armature conductors. Everything is there. When poles are rotating, conductors are stationary. But poles are rotating. Rotor poles are rotating. They cut the flux. EMF is induced in the armature winding. That can be taken from the stator terminals. That can be taken from the stator terminals. RYB. Along with the neutral. R phase, Y phase, B phase, and neutral also. Star connected alternator. No? Yes. This is the power output. Power output. Okay. Stator windings are distributed throughout stator periphery. Why I am explaining this once again? Because some students came, their doubts is after completion of the alternator, their doubt is like this. Sir, we are giving, there are two windings are there. One is field winding, another one is armature winding. Field and armature. In which winding EMF is generated? Tell me, in which winding EMF is generated? Is it in field winding or armature winding? Armature winding. Induced EMF will be in armature winding. Field winding is what for? To produce the flux. Produce the flux. Armature is high power circuit. Field rating is very less. Field rating is only, field rating is just a 0.2 to 0.5% of armature rating. Armature power conversion takes place. Mechanical power is converted to electrical in armature winding. EMF is induced. Because armature voltage is order of kilovolts. Kilovolts. Okay. Current is also kiloamperes. 10 kiloamperes, 20 kiloamperes armature current. So conductor, armature conductors are large number and they are thick conductors. EMF induced there is order of kilovolts. Currents also kiloamperes. But what about field winding? Field winding is low power circuit. Field current is order of some 20 amperes, 100 amperes. Voltage also 300 to 400 volts. That's all. Low power circuit. That is, field winding is just to produce a flux. Flux is the medium through which power conversion takes place. Na? You want to convert power mechanical to electrical or electrical to mechanical. Magnetic field is required. Who is producing the magnetic field? The DC excitation. Okay. So power is generated in the armature winding. That armature is kept on the stator. Sometimes you can also keep on the rotor. That is also we are going to see. But armature winding kept on the stator. We are going to see later advantages of stationary armature. If you keep armature winding on the stator, what are the advantages? If you keep on the rotor, what are the advantages? That also we are going to see. Okay? Yeah. This is about construction of alternators. Now, the static excitation means what we will do. Static excitation means this is AC, we are getting the AC. Static AC is converted to DC by using rectifier. This AC converted to DC by using rectifier, and the DC will be given to the field wind. A part of that power. Anyhow, this AC power is hundreds of kilowatts, megawatts. But by using step down transformer, voltage also 11 kV, 20 kV. Na? I need hardly 10, 20 kilovolts generated EMF. But field winding required hardly 300, 400 volts. So by step down transformer, the AC will be stepped down. A part of the power, I will take a closed loop system. I will take a part of the current. Parallelly, I will connect a transformer, and with that convert it to DC, and it will be given. That is by using static excitation. Static excitation by using a rectifier. AC converted to DC, that will be given. So please go through in the material. You can understand easily. Okay. Yeah. Now, lastly, advantages of stationary armature. So here I am keeping winding on the stator, na? Right? But instead of that, if you keep on the rotor, what will happen? Advantages of stationary armature. This diagram, stationary armature only. If you keep this winding on the rotor, what are the disadvantages? So let us see, the next topic is advantages of stationary armature. Yeah. Advantages of stationary armature. Okay. Advantages of stationary armature. Next topic is advantages of stationary armature. I will draw the two diagrams. I will draw the stationary armature and also rotating armature so that you can find. In salient poles, okay, salient pole rotor. The shaft. To that prime mover is coupled. This is a prime mover. This side exciter. The field winding is a field winding like this. Okay. Based on the field current, this act as a north pole, this act as a south pole, north pole and south pole, south pole. But all armature conductors are kept on the stator. Armature conductors are kept on the stator. Okay, this armature winding. EMF is induced in this armature winding. These are the main conductors, armature conductors. EMF is induced in these conductors, but they will be collected by the stator terminals R, Y, B and N. R, Y, B, N. These are the R, Y, B and N stator terminals. This is rotating armature, stationary armature. This one is stationary armature. Stationary armature, rotating field. Rotating field or poles. Rotating field, that is the poles, rotating poles. Let me draw stationary poles, rotating armature. Armature is rotating, say. These are the poles. Poles are fixed to the stator. Poles are fixed to the stator. And this is armature core. But on this, you can find multiple theoretical questions. Theoretical problem is directly formula based. At the same time, concept oriented. This is itself a this is a pole. This is also another pole, salient pole. The pole. The shaft. Driven with the prime mover. Prime mover. And on this armature winding, these are the slotted area. Slotted area. All the slots are made. In that armature winding can be kept. Okay. Shaft. But here there will be slip rings. 1 slip ring, 2 slip ring, 3 slip rings, 4 slip rings. The armature winding. The armature winding can be kept on the stator. These armature conductors, no? These are armature winding. Armature winding is rotating. And they will be connected like this. This is R, Y, B and N. R, Y, B, N. Is rotating armature. But how field winding is connected? This is the field, say, DC excitation, no? Yes. With that, they are kept like this. The winding can be, it is kept on this pole. Field winding. Field winding. Again, it can be brought negative terminal. Okay. So this is plus and minus. DC current, field current. Based on that, see, it may be acting as north pole, it acts as south pole. South pole. So this is an example of rotating armature, stationary field. Rotating armature, stationary field. Stationary field. Yeah. Okay, quickly, and then after this we will go for a break. Right. Okay. First, I will explain all the things and I'm going to write one by one step. But only your attention is needed. Yeah. Are you ready? Can I start now? Yeah. Class will be up to 1 o'clock. Yes. Class will be, I will continue up to 1 o'clock. Okay. Listen. See here. The first one. I can share the slides. I can also share these slides. Don't worry. Yes, listen. Now stop writing, listen to me, Okay, see, one is with stationary, this is stationary armature and this is rotating armature. Please stop writing. Stationary armature, rotating armature. With normally we will prefer this type, stationary armature is preferred over this rotating armature. But let us see what are the advantage of this stationary armature. Number one, first one is current collection is easy, current collection. Reason is the voltage. What is the armature voltage rating? Armature voltage current is 10 kiloamperes, order of kiloamperes. It is order of kiloamperes. Armature rating is order of kiloamperes. And voltage is kilovolts. Like 10 kiloamperes, say 10 kiloamperes and like some 22 kilovolts. Armature rating is very large, high power circuit. But whereas field rating is only order of hundreds amperes. Field voltage 300 to 400 volts DC. 400 volts DC. Current is order of 100 amperes. Order of 100 ampere, 100 or 200. But here it is 10 kiloamperes, 20 kiloamperes, very large. Main advantage is current collection is easy. If armature winding is kept on the stator, listen, when armature is kept on the stator, you can tap the power easily. Directly you can tap the power without using any slip ring and brushes. Because armature winding on the stator, EMF is induced, same can be tapped directly. So first point is current collection is easy. Number one, current collection is easy. If you want to correct the current, what is going to be happen here? This is armature is rotating, this is armature rotating. But you need to correct the current from rotating conductors through slip ring and brushes. See here, these are the slip ring and brushes. 4 slip rings are there, 4 brushes. But collecting order of 10 kiloamperes, 10 or 20 kiloamperes, they are the sliding contact, slippery. Slip rings, slippery, sliding contacts. So they will cause sparking at the brushes. Highly difficult to correct the current of order of kiloamperes, highly difficult. So current collection is easy here. Current collection is difficult. Number one, first point. Second advantage is stationary armature can be insulated easily and effectively for high voltages. Stationary, if armature winding is stationary, see, if it is once stationary means what we will do, first I will keep the insulating material. If I want, I can go for a higher slot depth. I can increase the slot depth. Slot width also can be increased. And thicker insulation can be kept here. And inside of that, I can keep the conductors. Insulation can be insulated easily and effectively for high voltages. Kilovolts and high voltages. Stator side, you can increase slot depth. Slot width can be increased. Stator diameter increases, no problem. But rotor increases, speed reduces. Okay. Stator side more flexibility. So armature winding can be insulated for high voltages easily and effectively for high voltages. Insulation is easy. But whereas with rotating armature, say in this diagram, rotating armature, what will happen? You want to keep the more conductors, same number of conductors on the left side diagram, whatever I have given. If I want to keep the same number of turns here, say for same rating, there slot depth has to be increased. More number of conductors you have to keep, now depth has to increase. If you increase the width, the rotor diameter becomes very, very large. So that's the reason what to do. We have to increase the depth of the slot. You have to increase the depth of the slot. So in that you need to keep. But when depth of the slots are increasing, rotor becomes mechanically weaker, no? Rotor becomes mechanically, it is weaker. We are cutting all the portion. Rotor portion you are cutting and inside you are keeping. But throughout 360 degrees, when you are cutting, rotor becomes mechanically weaker. It's mechanically weaker. Right? So since it is rotating at thousands of RPM, na, rotor becomes mechanically weaker. That is another drawback. Okay. That's the reason they are not used for large, small rating of the machines. For same rating, so rotor becomes mechanically weaker. And insulation also you cannot keep. The thicker insulation if you keep, rotor diameter increases. So all restrictions will comes into picture. But stator side happy. Okay. And another advantage is, see, how many slip rings are required here? With stationary air, first diagram, how many slip rings are required? 2 slip rings are enough for DC excitation. I am giving DC excitation. Na? So for DC, how many? 1 is plus, 1 is minus. 2 slip rings only on left side, stationary armature. But whereas how many slip rings are required here? 4 slip rings are required. 4 slip rings, that RYBN. Armature is 3-phase winding is rotating. 3-phase with star connected. 4 slip rings are required. Whereas here 2 slip rings. That to be 4 slip rings number wise is more. Rating of slip rings also more. Thicker slip rings are required. That is another disadvantage. Only 2 slip rings this side. Advantage. Next, definitely we have to keep deeper slots here. Right side diagram, rotating armature, slot depth should be more in rotating armature. When slot depth is more means more leakage flux. Na? Yes. You know, leakage flux is proportional to what? Depth of the slot. Depth of the slot. Inversely proportional to width. I think you are knowing in induction motor, no? Yes, depth. Deeper slots are required with rotating armature. When deeper slots means more leakage flux. More leakage flux, more leakage reactance drop. Voltage drop is more with rotating armature. Regulation is poor. But in this, if you take stationary armature, first diagram stationary armature, slot width I am increasing, not depth, width. Then width means less leakage flux. Less leakage flux, less leakage reactance. Less leakage reactance drop, better the regulation. Regulation is better with the stationary armature. Regulation is better compared with this. And also another advantage is stationary armature can be cooled easily and effectively. Stationary armature cooling is easy, no? Stator side, I can provide the cooling ducts. Cooling ducts can be provided here. Cooling ducts can be provided. Cooling ducts. Cooling ducts means air passages. Okay. We'll cut that portion. In that, we will send the cooling medium. This is cooling medium is passes. Hydrogen cooling. Conductors are like this. On the stator periphery, cooling ducts can be provided. And cooling medium, hydrogen is passing hydrogen gases. Then they will, what that hydrogen will do? It will absorb the heat. It will absorb the heat by the armature winding. Because heat is produced by I square R loss, copper losses. The copper losses will produce the heat, but nearby when hydrogen gas is passing, it absorbs the heat. And that hot gases are continuously cooled and cold gases will be circulated. But that is easy on stator side. Na? Stator side, whatever you want, you can do. But when rotor is rotating, winding is kept on the rotor, can you send the cooling medium? Not possible. Can you provide the cooling ducts? Not possible. Okay, hydrogen with a pipe we have to keep. But here, first diagram, I can simply, this is a cooling duct is there. There I can keep a hydrogen pipe, gas will circulate. But this is rotating. In rotating, how can you send the cooling medium? No. Forced cooling is not possible. Forced cooling at a gas, we are pumping gas, but here it is not possible. Okay. Cooling is effective. What I meant to say is cooling is easy and effective. Cooling is easy and effective with stationary armature, but it's difficult here. Difficult. Okay. Yeah. Next. In these two cases, which will have diameter of rotor light weight of the diameter with stationary armature. First one with stationary armature, the rotor is lightweight because field is rotating. Rotor is lightweight. Rotor is lightweight. But here rotor is heavy size. Armature is circulating heavy rotor. But here lightweight. When light rotor, in the case of stationary armature, rotor is light in weight. Higher speeds are possible. We can go higher speeds. Then higher speeds means rating of the machine is more. Okay. So these are the advantages. Of course, in this diagram, I have taken salient pole machine only. Salient poles are rotating, but here salient poles are fixed to the stator. Similarly, you can write cylindrical rotor also. Okay. But rotor is lightweight. Higher speeds are possible compared with this. Therefore, what we have done with stationary armature is high power circuit that is kept on the stator always best. Okay. So each and every point is itself objective questions. Multiple select answers. You will give a set of statements. You have to find all statements correct or not. So let me write all these things and after that we'll go for break. Advantages of stationary armature. Number one, first one, current collection is easy. Current collection is easy. Current collection is easy from stationary armature terminals. From stationary armature terminals. Whereas with rotating armature, the current has to collect through the brushes. The current has to collect through the slip ring and brushes, no? Through the slip ring and brushes. Through the slip ring and brushes, which will causes sparking at the brushes. Sparking at the brushes. Right? Yeah. Second advantage is stationary armature can be insulated for high voltages. Stationary armature can be insulated easily and effectively. For high voltages. Right? Because on stator side, if we keep rotor side, it also has to, right, face the centrifugal forces. It is kept on the rotor, thicker insulation and it has to be subjected with centrifugal forces. Stator side better for high voltages. Stationary armature can be insulated easily and effectively for high voltages. Next, 2 slip rings are required. Third one, only 2 slip rings are required. Only 2 slip rings are required for stationary armature. Whereas 4 slip rings with the rotating armature. With rotating armature, 4 slip rings, no? 4 slip rings. Next. Slot depth is less. Slot depth is less. Less compared with or let me add this point better. What is that? For rotating armature, deeper slots are required. Deeper slots are required. Deeper slots are required to accommodate the armature winding. Deeper slots are required. Therefore, rotor is mechanically weaker. So rotor is mechanically weaker. This is disadvantage of rotating armature, no? But that will be advantage. What is advantage with stationary armature? Armature is stronger. Rotor becomes mechanically weaker with rotating armature. But with stationary armature, armature winding is, rotor becomes weaker, no? Yes. But with stationary armature, it is good. It is a drawback in the rotating armature. Next, fourth one is fifth one, less slot depth compared with less slot depth. Therefore, less leakage flux. Less leakage reactance. Therefore, less leakage reactance drop. For better the regulation, better will be the regulation. Regulation is better with the stationary armature. Regulation is better. Next, sixth one. Stationary armature can be cooled easily. Stationary armature can be cooled easily and effectively. By providing cooling ducts. by providing cooling ducts. Cooling ducts. Okay, yes. Hydrogen cooling is best. Hydrogen cooling. Normally, hydrogen cooling can be used. Providing cooling ducts. Next, rotor is light in weight. Rotor is light in weight. Light in weight. Therefore, higher speeds are possible. Higher speeds are possible. Therefore, rating is more. Rating is more for rating is more with the rotating armature, with the stationary armature. Stationary armature. Okay. Rating is more with stationary armature. Rotor is lightweight, higher speeds are. So these are the advantages of stationary armature. Okay. Yeah. Yes, completed. Now, shall we take the break for some time? Yes. Take the break for some time. Okay. Voice is not coming, huh? Yeah, I think there may be some problem. I hope now it may be fine. Okay. I will check. Okay. Right? Break, how much time you want? How much time break? Once again, you type it. Break. Voice is good, huh? Okay. Sometimes it may be network problem. It may, so you can feel. Fine, fine. Okay, 15 minutes. Some people are asking 30 minutes. 1 hour break, huh? 1 hour instead of that, it may be better to close the class now. Okay. So via media, we will take around 15 to 20 minutes is best. After having class 1.5 hour, not tiffin break. So 20 minutes, that is reasonable. 20 minutes until some relax. System is required some time. So 20 minutes break you take. And after that, we are going to derivation of EMF equation. After the break, we will see derivation of EMF equation. 20 minutes break. And class will start again. Class will be up to 1 o'clock. 1 o'clock. So class is now it is nearly 11:15. Yes. 11. We are going to start nearly 11:30 for 11:35. 11:30 roughly. Okay. Take break. Relax because highly difficult. After breakfast, system normally dull. Break is essential. Okay. Take the break and then after that we'll continue. Okay. Okay. Yeah. Right. Are you ready? Time up. Yeah. Okay. Some of the students are raising a doubt, like in cylinder. Normally, practical machines, which type of excitation are used? Which type of excitations are used? Brushless excitation. Brushless excitation, there is no brushes, no slip rings, nothing. Practically, generating stations, brushless, it may be cylindrical or salient pole machine, brushless excitations. There is no slip rings, there is no brushes. This is one method I have shown. What is that? The DC exciter, slip rings will be there. Okay. Brushless excitation, there is no question of slip rings and brushes. Just to go through that, the material you see. So, I think there is a diagram with brushless excitation. Brushless excitation. This is cut side, na? Inside. Yeah. The inside itself, diodes are there, na? Permanent magnetic rotor will be there. Permanent magnet generator. AC generator. Permanent magnet AC generator. Okay. Stationary armature rotating field. This is brushless excitation. Method brushless excitation. See this? This is the brushless excitation system. Diode wheels. There will be permanent magnet. Okay. You just go through the material because I cannot explain this. If I explain this, another time will take place. Time is limitation for you. Main gate examination is important. I have given the material. You please go through that. The material you can see. What I mean to say is, in practical generator, there is no slip rings and brushes. Brushless excitation that can be used. Just a minute. 1 minute. Okay. Yeah. One student raise a doubt. What is that? Sir, cylindrical rotor alternator will rotate very high speed. So, but that will be given with DC excitation. Slip rings are required. Okay. On the diagram, I have shown with the slip rings by using DC generator. But practical cases, there will be brushless excitation. Brushless excitation, there is no brushes, slip rings. Okay. Now coming to the next topic. Next topic is EMF equation of alternator. EMF equation of alternator. Next topic is EMF equation of alternator. Simply EMF equation of synchronous machine. It may be generator or motor. EMF equation of synchronous machine. EMF equation is equal to 4.44 kp kd phi ft. 4.44 kp kd phi ft. And in that, just I want to make some important conclusions. How flux linkages takes place. Okay. Yeah. See, take down this diagram. This is one pole. North pole. Okay. In this armature winding, armature coil can be kept like this. The armature coil. Armature coil. Similarly, okay. Now, here coil, I would like to take for the coil, armature coil. But armature coil, we are taking for half rotation. Half rotation. Of course, there will be field. We are giving DC current, field current. Current is coming like this, no? Yes. This act as north pole. North pole. This is south pole. Here also it is north pole and south pole. In this, we are going to see some important conclusions. Important conclusions. Okay. Let us take this is at omega t is equal to, this is instant one. Omega t is equal to 0 degrees. This is omega t is equal to 90 degrees. A coil has been rotated 90 degrees. Position 1 to position 2, if you take position 1 to position 2, omega t is equal to 0, position 1 say, and another instant. That is, this is the first instant, and this is the second instant. At first instant, omega t is 0, coil is like this, and coil has rotated 90 degrees. 90 degrees. Okay. Fine. See, dear students, I have taken like this. For example, this is the rotor core. No? This is a rotor core, armature core. Armature core. In this is one pole. This is a pole, right? This is a pole. This is another pole. Another pole. On the rotor, we are keeping a conductor. So for example, this is one conductor, this is another conductor, say. One conductor, another conductor is like this. coil. But when rotor rotate, what is going to be happen? When rotor, it will rotate now. I am taking rotating armature. You can take any one. Rotating armature, coil is rotating. It is easy for visualization. So when coil is rotating, at first instant, coil is under the pole. The coil is in between the poles. But here coil is under the poles. Machine is kept vertically. Yeah. For your kind information, machines, how they will be mounted? They will be hydroelectric power station. Alternates are mounted vertically. They will be like this. These are rotor, na? They are mounted like this. Prime mover will be here. It will rotate it. Prime mover here. Water is coming through the penstock. Water hit the turbine. Then turbine rotate. The generator also will rotate. After hitting the water, water is released into the tail race. So that water cannot come to the generator room. Hydro power station, generator room is separate, hydro turbine room is separate. Bottom floor is a turbine, top floor is a generator. But both are mechanically coupled through the shaft. So first water will come, water hit the turbine rotate, then generator rotate. But after hitting that turbine, water released into the tail race. Okay? Yeah. Thermal power station, alternates are mounted horizontally mounted. They rotate like this. Hydro, vertically. But here, for easy understanding purpose, I am taking machine is mounted vertically. Coil is also vertical. This is the coil side. This is a coil. Yes, this is a coil. In first diagram, instant one, I am keeping coil like this. One pole is here now. See, one pole is here. Other pole is here. Like this is a pole, say for example. This pole, this is one coil. Another pole is this side. At instant, coil is in between the poles, not under the pole. Pole is here. Coil is not exactly under the pole. Conductor is not along the direct axis. Conductors are along the quadrature axis because pole is here, not quadrature axis. And here coil is rotated 90 degrees. Now the coil is under the poles. In these two cases, flux linkages and induced EMF. See, flux direction. The flux lines are like this. The flux lines, these are the flux lines, no? All the flux lines are passes. Let me change the color. The flux lines are, let me use another color. All flux lines are passes from north to south. Flux lines. These are the flux lines. All the flux lines are passes inside of the coil. Correct? Color is almost the same. Okay, let me use green. Flux lines. These are the flux lines. All flux lines are passes inside of the coil. Okay. At instant one, right? See here. Now stop writing. This is the coil. Coil is kept like this. Pole is here. When pole is here, okay. This is the pole shoe say. All flux lines are passes inside of the coil. That is flux linkages is maximum. So flux linkages is nothing but flux passing through the coil. Na? Yes. Once again, I am writing flux linkages means flux passing through the coil. That is flux passing inside of the coil. passing inside of the coil. Inside of the coil. So therefore, at this position, all flux lines are passing inside of the coil. Because pole height is equal to coil height, concentrate. Now I am going to continuity. Listen to me. When pole height is equal to pole also same height, this is the pole. Pole height is equal to coil height. Pole pitch also equal to coil pitch. How much pole pitch? This is pole pitch. Pole pitch is nearly 180 degrees. 180 degrees. Pole pitch is equal to 180. And coil is also same pitch. Dimensions are same. Pole height is equal to coil height. Pole pitch is equal to coil pitch 180. So all flux lines are passes inside of the coil. Inside of the coil. Flux linkages is maximum. This is the maximum flux lines will passes. So flux linkages is maximum. At this instant, flux linkages. Flux linkages. That is psi. Flux linkages is maximum. Psi is maximum. Since all flux lines are passes inside of the coil. I will write the statements later. All flux lines are passes inside of the coil. That's the reason flux linkages is maximum. Okay, because all flux lines are passes. All flux lines are passes inside of the coil. All flux lines passes inside of the coil. Inside of coil. Therefore, flux linkages is maximum. All flux lines are passes. But are they cutting the? Are the flux lines are cutting the conduct coil sides are cutting the flux lines? No, coil sides are not cutting. Though all flux lines are passing, when conductors moves, they will move parallel. They will move parallel to the flux lines. The coil sides are moving parallel to the flux lines. If you take here tangential direction, they are moving parallel to the flux lines. So no flux cutting action. Therefore, no induced EMF. No flux cutting, no induced EMF. All flux lines are moving parallel to the flux lines. All flux lines are moving parallel to the flux lines. Parallel to flux lines. Therefore, no flux cutting. No flux cutting. For no induced EMF. No induced EMF. So EMF is proportional to d psi by dt. Induced EMF is proportional to d psi by dt. Therefore, EMF will be 0. Induced EMF is proportional to d psi by dt. That is minimum. Minimum. So EMF is 0. Therefore, E is equal to 0 here. Though flux linkages is maximum, flux linkages psi is maximum, but induced EMF is minimum. Induced EMF is 0 at instant 1. Instant 1. Now let us see instant 2. Instant 2. At second instant, here they are not cutting. All flux lines are passes, but no cutting. Whereas, see here, all flux lines are passes outside of the coil. All flux lines are passing outside of the coil, not inside. See, when coil is like this, now here we are keeping coil like this, but pole is here. Pole is here. All flux lines are passing outside of the coil, side of the coil, not inside. Not inside. If coil is here, flux lines are going to be maximum. Pole is this side, na? Pole is here. One pole is here, another pole is here. So all flux lines are passes outside of the coil, not inside. So flux linkages is minimum. Minimum. Incante coil width is 180 degrees, na? But this is one conductor kept under that slot. This is kept under one slot. But all flux lines are passing outside of the coil. So flux linkages is minimum. Flux linkages is minimum. All flux lines are passes. Flux linkages is minimum. Minimum. That is psi is equal to 0, say here. Psi is equal to 0. Because all flux lines are passes outside of the coil. All flux lines are passes outside of the coil. All flux lines are passes are passing outside of the coil. Outside of coil. Therefore, flux linkages is minimum. Flux linkages psi is minimum. Is minimum. Flux linkage is minimum. But the moment when coils moves, coils are continuously rotating. Coils are not stationary. Coils are continuously rotating. It's continuously rotating. But at this instant, when coils are rotating, tangentially how they can move? Perpendicular to the flux lines. Perpendicular. Their coil sides moves perpendicular to the flux lines. Perpendicular. Perpendicular means here parallel, no? Parallel. But in the second diagram, perpendicular. So flux cutting is maximum. One coil is they are moving perpendicular to the flux lines. Perpendicular means maximum flux cutting action. Therefore, induced EMF is maximum. So here, though all flux lines are passing outside, the instant when coils are moving, they cut the flux by 90 degrees. So flux lines are moving. Not flux lines, are conductors, coil sides. Here also, please correct it. All flux lines are all, not all flux lines. Please check it. Moving parallel to the flux lines. Coil sides. Coil sides are conductors. Please correct it. First diagram. First one. We're getting here. I have written flux lines, not flux lines. All coil sides. Coil sides are conductors, are moving parallel to the flux lines. Whereas here, the coil sides are conductors. Coil sides are conductors. Or conductors are moving perpendicular to the flux lines. Perpendicular to the flux lines. Perpendicular to flux lines. Therefore, maximum flux cutting action. Maximum flux cutting. Therefore, maximum induced EMF. Maximum induced EMF. Therefore, E is maximum. Induced EMF is proportional to d psi by dt, na? Yes. D psi by dt means cutting. E is proportional to d psi by dt. That is maximum. E is maximum. Psi 0, but E will be maximum. So here flux linkages is minimum, but induced EMF is maximum. Induced EMF is maximum. So if you draw the variation of these flux linkages, so coil is here, omega t is 0 say. When coil rotated 90 degrees, for 90 degrees, flux linkages changes from maximum to minimum. Sorry. Flux linkages changes from maximum to minimum. So let me draw the variation of flux linkages. Variation of flux linkages. Variation of flux linkages. This is psi. Psi flux linkages with respect to omega t. With respect to omega t. This is psi, say psi flux linkages. At omega t is equal to 0. If you take it omega t is equal to 90 degrees, and again at omega t is equal to 180 degrees. 180 degrees. So flux linkages is maximum at omega t is equal to 0 maximum, but flux linkages at omega t is equal to 0. 180 degrees it is again negative maximum. Negative maximum. Negative. Why negative maximum means this is plane of the coil. Say it is all flux lines are passes maximum. After 90 degrees, it is again 0, 0. Again 180 degrees, it is maximum. And earlier this is passing this side, but after one rotation, it is passing this side. So this plane, if you take positive with respect to this plane, it is negative. Negative. Okay. Join these things. Yeah. This is the side. Flux linkages. Flux linkages is a cos wave. Cos wave. No? Yes. Flux linkage is proportional to cos omega t. Cos wave. Whereas induced EMF, if you take, induced EMF will be sin omega t. When omega t is equal to 0, induced EMF 0, omega t 90 0, 180 again it will be 0. This is induced EMF. This is E, whereas this is psi. This is psi. So now I can write. Can I write this flux linkages is proportional to cos omega t? Yes, because it is a cos wave. Flux linkages is proportional to cos omega t. And that flux linkages is equal to phi into cos omega t. Phi into cos omega t. Equation 1. Where phi is the flux per pole. Where phi is the flux per pole, that is constant. Why? Because DC excitation, it is DC excitation. Phi constant. Field current constant, flux constant. Okay. Phi omega t, phi is constant. Now, but that psi is different. Dear student, just a minute. See this diagram. See to me. See to me. So my flux is coming from this pole is 20 milliweber. Say this is a pole. This is a pole pitch and this is pole core. No. This is a pole. Say my hand is a pole. 20 milliwebers is producing. 20 milliwebers is passing. Psi is equal to phi into cos omega t. Phi 20 say at this instant what is the psi? 20 into cos 0. 20. All flux lines are passes. 20 maximum. When it is rotating some angle, say some angle. This is 20 only. 20 into cos 60. After 60 degrees, say 20 into cos phi 20. 20 into cos 60, how much? 10. Psi reduced, but phi is constant. And when it is rotating 90 degrees, flux is 20 milliweber, say, but all 20 milliwebers are passing outside of the coil. So then psi is equal to phi into cos 90. Psi is 0. Psi is 0, but phi is 20 only. 20 into cos 90 is 0. So that's the reason phi is constant. Constant. Okay. Yeah. Now, according to Faraday's law, induced EMF is equal to what? According to Faraday's law. According to Faraday's law, the magnitude of induced EMF is equal to minus T into d psi by dt. Minus T into d psi by dt. Where T is the number of turns. Let me use T. T is the number of turns. That is equal to minus T into d by dt. Psi is equal to what? Phi into cos omega t. Phi into cos omega t. That is equal to, this is equal to T into phi into omega into sin omega t. Correct? Cos omega t, differentiation sin omega t. Minus sin omega t. Minus minus plus. Is equal to T into phi. Omega is 2 pi f. Omega is 2 pi f. And sin omega t. Omega I am writing 2 pi f. That is equal to 2 pi phi f t sin omega t. 2 pi phi. Rearranging the terms. 2 pi phi. Same thing only I am writing 2 pi f t. This is equal to E maximum sin omega t. E maximum sin omega t. E is equal to E maximum sin omega t. That can also be written as E maximum sin omega t can be written as cos omega t minus 90 degrees. Cos omega t minus 90 degrees. minus 90. So let us take, this is equation number 2. This is equation number 3. Equation number 3. But where E maximum is equal to 2 pi phi ft. 2 pi phi ft. 2 pi phi ft. By comparing that equation, 2 pi phi ft. But RMS value, E RMS, always we will take RMS value. E RMS is equal to E maximum divided by root 2. E maximum divided by root 2. That is equal to how much? We will get root 2 into pi phi ft. Root 2 into pi phi ft. That is equal to 4.44 phi ft. 4.44 phi ft. That is itself E. Therefore, induced EMF equation, E is equal to 4.44 phi ft. Is the EMF equation for concentrated winding. But distributed winding EMF equation is 4.44 kp kd phi ft. This is for EMF equation. Equation for concentrated winding. But what about distributed winding? Distributed winding 4.44 kp kd phi ft. Kp kd will comes into picture. Kp kd will comes into picture. So let me write in the next page. Yeah. So EMF equation. Right. See, the EMF equation is equal to E is equal to 4.44 phi ft. 4.44 phi ft. This is the EMF equation for concentrated and a full pitch winding. For concentrated and full pitch winding. And full pitch winding. Concentrated and full pitch winding. But practically, winding is never be concentrated, never be full pitched. It is always short pitch and distributed winding. Short pitch, distributed. Short pitch and distributed winding. So E is equal to actually 4.44 kp kd phi ft. This is EMF equation. Simply kp kd will comes into picture. EMF is reduced by pitch factor, distribution factor. The EMF equation for distributed winding, distributed and short pitch winding. Distributed and short pitch winding. Distributed and short pitch winding. Short pitch winding. Where kp is called, T is the number of turns. T is the number of turns. F is the frequency. Frequency in hertz. Where phi, what is the phi? Flux per pole. Average value of flux per pole. Average value of flux per pole. Flux per pole. In Webers, na? Yes, in Webers. KD is the distribution factor. KD is the distribution factor. KP is the pitch factor. KP is pitch factor. E is induced EMF. E is the induced EMF in volts. Induced EMF in volts. Induced EMF in volts. Is a EMF equation flux per pole, average value of flux per pole. Same equation you might have seen in transformer also. But in transformer, what is the phi? Maximum value of flux. Maximum value of flux. There is no poles, nothing in transformer. But here, flux per pole. You take phi flux per pole. DC flux, anyhow, it is average flux only. Na? The DC flux, average flux per pole. Okay. Look at this carefully. This equation 1 and equation 2. By observing equation 1 and equation 2 and 3, if equation 1 flux linkages, is the flux linkages is a cos omega t. Phi is equal to phi into cos omega t. But whereas induced EMF is E is equal to E maximum sin omega t from equation 2. E maximum sin omega t. Third equation, E maximum cos omega t minus 90. So what is the meaning of that? Flux is a cos wave, induced EMF is sine wave. And comparing equation 1 and 3, flux linkages is phi into cos omega t, but induced EMF is cos omega t minus 90. Means that induced EMF lags the flux linkages by 90 degrees. Induced EMF lags the flux linkages by 90 degrees. Okay. So let me write the statement. From equation, by observing the equations, see, from equation 1 and 3, it can be observed that the induced EMF lags. The EMF lags the flux linkages by 90 degrees. The EMF lags the flux linkages by 90 degrees. E lags the psi by 90 degrees. That is cos omega t minus 90. So whether it may be dynamical induced EMF or statical induced EMF lags the flux linkages by 90 degrees. Lags by 90 degrees. Fine. Okay. Flux constant only, but how change of flux linkages you are observing? Tell me from the diagram how change of flux linkages. This is my taken. Yes, this is the pole flux per pole constant. Flux 20 milliweber say. But when coil position is changing, what will happen? 20 milliwebers is passing. After some time, some 15 milliwebers are passing. When rotated, 10 milliwebers are passing. Now 5 milliwebers. At this position, 0. The flux constant, as coil rotation it changes, flux lines passes inside of the coil changes because plane of the coil changing. Plane of the coil is changing. So some flux lines will go outside, some flux lines inside. At this instant, all flux lines are passes. But after some time, some flux lines are going inside, some is going outside. So like when coil rotated 90 degrees, flux linkage is maximum. After 90 degrees, flux linkages is minimum. And for every 90 degrees rotation, flux linkages changes 100%. So flux linkages is created by relative motion, rotation. When coil is rotating, flux passing through the coil changes. Yeah. Let me add that point. Though flux is constant, since DC excitation, though the flux is constant, change of flux linkages is created. Change of flux linkages is created by rotation of the coil. Rotation of coil. For every 90 degrees, 100% change. For every 90 degrees, 100% change. Or 100% change of flux linkages. 0 to maximum. 100% change. Correct? Yes. 100% change. Okay. So this is about EMF equation. We are going to do the problems after finding KP, pitch factor, distribution factor. We are going to see the problems. Next topic is armature winding. Okay, EMF equation is completed. Now let us start the next topic. Armature winding. Okay. Next topic is armature winding. Armature winding. Armature winding. Armature winding is mainly, it can be divided into two types. Armature winding can be divided into two types. Number one, concentrated winding. It is concentrated winding and distributed winding. Distributed winding, concentrated winding and distributed winding. Concentrated, distributed. But concentrated winding is not preferred. Not preferred. Distributed winding is preferred. We are going to see why distributed winding is preferred. Again, among distributed winding, there are two types of the windings. There are full pitch winding, and short pitch winding. Full pitch winding and short pitch winding. Of course, full pitch winding is not preferred. Short pitch winding is preferred. Short pitch winding is preferred. Again, among short pitch winding, there are two types of windings. Integral slot winding, and fractional slot winding. Fractional slot winding, integral slot winding and fractional slot winding. For normal rating of the machines, integral slot winding also used. But large alternators which are used in generating stations, it will be fractional slot windings are used. Okay, fractional slot. But normally even 100 kVA, 200 kVA, integral slot winding also can be used. But megawatt alternators are there, no? They will be fractional slot winding. And some of the students will raise a doubt. Sir, winding is distributed, short pitch winding, both are separated? No. Winding is distributed, under that it will be short pitch, under that it will be fractional slot winding. Don't think distributed winding, one winding, short pitch winding is another winding, not like that. Winding is distributed, under that it will be short pitch, under that it will be fractional slot winding. Okay, yeah. So, in generating stations, how it will be? Winding will be distributed. Winding, the nature of the winding is distributed, under the short pitch, short pitch, and fractional slot winding. Fractional slot winding. Okay, is the nature of the winding. Winding is distributed. Under that it will be short pitch. Under that it will be fractional slot winding. Fractional slot winding. Okay. And first of all, why to have these many modifications in the armature winding? Why do you require these many, right? The modifications in the armature winding. Reason is to generate pure sine wave. To generate the pure sine wave means to eliminate the harmonics. Harmonics is the generated EMF. To eliminate the harmonics. Okay. But what are the reasons to harmonics? Reasons for harmonics. Yeah. This is because to eliminate the harmonics. All these things are because of to elimination of the harmonics. For elimination of harmonics. Elimination of harmonics. Harmonics. So that generated EMF is pure sinusoidal. Generated EMF is sine wave, sinusoidal. We want to generate pure sine wave. That's the reason we need to use all distributed short pitch and fractional slot windings. Okay. And what are the causes for harmonics? First of all, causes for harmonics. Causes for harmonics is mainly due to saturation. Saturation of the magnetic field. Let us see. So for example, the pole is a salient pole. In the salient pole, by chamfering the salient pole, what we have done, by chamfering the salient pole, the flux lines are like this, no? Flux lines are like this. Flux passes. Most of the flux passes at the center of the pole because air gap is minimum means most of the flux will be crowded here. Flux prefer minimum reluctance path, na? Yes. By chamfering the salient pole, we are expected flux distribution is going to be sinusoidal. Flux distribution, this is B wave, is sinusoidal. But at the center of the pole, flux is maximum. Na? At the center of the pole, flux is maximum. Therefore, this center portion will tend to saturate. Center portion will tend to saturate. Saturation takes place. Due to saturation, flux will not increase. Flux also becomes constant. Flux becomes constant. So now your flux is going to be like this. It is a flat topped wave, not exactly sine wave. Flux distribution is a flat topped wave. You will get flat topped wave. This is a type of waveform due to saturation. So that is consisting of harmonics, no? That is consisting of harmonics. When flux distribution is like this, induced EMF also same. Induced EMF also you will get the same shape of the waveform. So the main reason for the production of harmonics is non-sinusoidal flux distribution in the air gap is mainly due to saturation. Mainly due to saturation. Okay, yeah. The main reason for the production of harmonics, the main reason for the production of harmonics, is non-sinusoidal flux distribution. Non-sinusoidal flux distribution in the air gap. Flux distribution in the air gap. Non-sinusoidal flux distribution in the air gap is mainly due to saturation. Because center more flux is passing, it will tend to saturate. It's mainly due to saturation. It's mainly due to saturation. Okay, yes. And when flux distribution is like this, generated EMF also same, na? Yes, generated EMF also same. For example, this is B wave, say. Let me take B wave separately. Then generated EMF waveform also same. E wave also it will be same. E wave also, generated EMF also is same. Generated EMF it is also going to be flat top. E wave. This is with respect to space, sir. Respect to space. Or theta, say some angle theta. This is but with respect to time omega t. Omega t. Due to saturation. And this non-sinusoidal flux distribution, the non-sinusoidal flux distribution can be represented or EMF can be represented in sinusoidal functions. Generally, in the generator, you are generating flat top wave, na? Yes. But a flat top wave can be divided into sinusoidal functions. Sinusoidal functions with various magnitudes and various frequency. We are getting flat top wave, but the flat top wave can be analyzed. Flat top wave can be analyzed by using the sinusoidal functions. Sinusoidal functions. A non-sinusoidal waveform. A non-sinusoidal waveform can be divided into sinusoidal functions. Sinusoidal functions with various magnitudes and frequency. Various magnitudes and frequency. Various magnitudes and frequency. Okay, yes. According to Fourier analysis. According to Fourier series. According to Fourier analysis. Fourier analysis. So we can write B like that. B is equal to B1 sin theta plus B3 sin theta, sin 3 theta plus B5 sin 5 theta plus dash dash dash. Similarly, E is equal to E1 sin omega t. The induced EMF is omega t, time phase. Flux distribution is space displacement, space and theta, angle, theta. But this is time angle. E3 sin 3 omega t plus E5 sin 5 omega t plus dash dash dash. Okay. First of all, why we are dividing into sinusoidal functions? Tell me. Non-sinusoidal is divided into sinusoidal. Why? Because if analysis with sinusoidal is easy, sinusoidal waveform, integration and differentiation of sine wave is again sine and cos wave. Any non-sinusoidal waveform can be divided into sinusoidal functions. That is right, proved by Fourier. Fourier have shown Now I will take third harmonic, do its analysis separately. Fifth harmonic also sine wave, do analysis separately. But by taking a non-sinusoidal equation is difficult. Single equation not possible, but it can be divided into different sinusoidal functions. But first one is called fundamental. No, this is fundamental. All others are said to be harmonics. This is a fundamental. Rest of the things are said to be harmonics. So just I want to show here how this non-sinusoidal can be divided into sinusoidal functions. How? What we are doing is this waveform only we are writing like this. This waveform we are writing like this. And this waveform we are writing like this. A non-sinusoidal can be divided into sinusoidal functions. How it is valid? Let me prove that. If you add all these sinusoidal functions with various magnitude, again you will get flat top. Again you will get flat top. Hence it can be proved conversely correct. Let me show that. See, this is fundamental. Fundamental is a sine wave. This is a sine wave. No? Fundamental is a sine wave. Fine. E1. But third harmonic voltage will be 3 half cycles. 3 half cycles. This is 1. Three half cycles. This is E1 fundamental, but this is third harmonic E3. If you add both, the resultant will be how resultant of these two. The resultant will be E1 plus E3. If you add E1 plus E3, this is E1 plus E3. Up to this point, both are adding, na? Yes, both are adding. This increases. But at the center, one is positive, other one is negative. It will reduce. And again here both are increasing. So this waveform is E1 plus E3. E1 is sine wave, E3 also sine wave. Up to here, both are positive. Na? Up to here, both are positive. So both are increasing. But at the middle, one is positive, other one is negative. Net reduces. This side also, both are positive, increases. E1 plus E3 is non-sinusoidal. You are getting flat. Non-sinusoidal. If you add fifth harmonic, you add fifth harmonic component. Fifth harmonic will have 5 half cycles. This is 1. 1, 2, 3. No, 1 minute. Yeah, this is 1, 2, 3, 4, 5. Yeah, I am taking fifth harmonic components. Fifth harmonic components. This is E5. E5, let me add E5 to the E1 plus E3. Add E1. E1 plus E3 already there. For that you add E5. Add E5. So by adding E5, if you add E5, it is going to be like this. Up to here both are positive, na? Up to here both are positive. And here both are one positive, one negative. This is fundamental. Okay. Now, if you add here, both are adding. Okay. So due to this, I'm adding E1 plus E2 to E3. Up to here, both are positive. Net increases. Here, net decreases. Again, net increases. Net decreases. Like this. This is E1 plus E3 plus E5. So observation is mainly what we are observing is flat is increasing. No? Flat is more flat. If you see E1 plus E3 flat. Third harmonic added, but fifth harmonic more flat. If you add seventh harmonic, still it is going to be more flat. If you add seventh harmonic, it will be still more flat. Add seventh harmonic, say it becomes like a flat top wave. Seventh, say, for example, it is E1 plus E3 plus E5 plus E7, like that. More harmonics. Only odd harmonics will generate. No question of even harmonics. Even harmonics won't exist. Odd harmonics only. So it is proved that a sinusoidal waveform can be divided into non-sinusoidal can be divided into sinusoidal functions. Okay? Yeah. A flat top wave can be divided into sinusoidal functions with different frequencies. If you add all E1 sin omega t plus E3 sin 3 omega t plus E5 sin 5 omega t, then you will get a non-sinusoidal flat top wave. You will get flat top waveform. So hence it is proved flat can be divided into sinusoidal functions, because if you add all that, you will get flat top. So I have shown both. Okay. Fine. Right. I would like to take only fifth harmonic. Say, for example, fifth harmonic. Is a fundamental. Yeah, this is a fundamental. Fifth harmonic will have 5 half cycles. No? Yes, 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. This is fundamental. Whereas this is fifth harmonic. Fifth harmonic. The fundamental pole, this is due to north pole, say, but there are 5 north pole, south pole, north pole, south pole, north pole. Because each half cycle is due to one pole. If you take, there are 5 half cycles, means 5 north poles. Therefore, fundamental poles, nth harmonic poles are n times. Angles. If you take angles, this is angle is 180 degrees. That 180 degrees is fundamental angle. That is the fundamental angle. 180 degrees electrical. Fundamental angle. But whereas this is harmonic angle, positive half cycle, this positive half cycle is also, this is 180 degrees, no? This is 180 degrees. This also 180 degrees. This also 180 degrees. This also 180 degrees. This also 180 degrees. These are said to be harmonic angle. This is harmonic angle. Harmonic angle. Okay? Harmonic angle. From this, what I want to convey, number of poles. Under one fundamental pole, there are 5 poles. 5 poles are there. 5 fundamental poles are there. Angles also. One fundamental angle 180 degrees, 5 180s. Angles for nth harmonic also n times. Frequency also n times. Frequency also n. So frequency of nth harmonic n times of fundamental frequency. And poles also. Fundamental poles n times of fundamental poles. Angle also n times of fundamental angle for nth harmonic. Right? Nth harmonic frequency n times. Fundamental nth harmonic poles also n times. Nth harmonic pole P suffix n. Nth harmonic poles also n times. Nth harmonic angles also n times. Okay. Yeah. These concepts are required at the time of short pitch winding. When we are drawing short pitch winding. Okay. And coming to harmonics, there only odd harmonics will generate. No question of even harmonics. Only odd harmonics that will generate. No question of even harmonics. Harmonics are fundamental harmonics. First one is called fundamental. Third harmonic, 5th, 7th, 9th, 11th, 13th, 15, 17, 19, 21, 23, 25, dash, dash, dash. Only odd harmonics will generate because even symmetry, only odd harmonics generate. Odd harmonics will generate. Only odd harmonics will generate. Even harmonics won't exist. Because it is due to even symmetry. Even harmonics will be, they won't exist. Due to even symmetry. Even harmonics won't exist. Will not exist due to even symmetry. Even symmetry. Even symmetry means positive half cycle is same as negative half cycle. Na? This is positive half cycle. Negative half cycle also same. As long as positive half cycle, negative half cycle is same, there is no even harmonics. They will get cancelled actually. Even harmonics, as long as, of course, both may be non-sinusoidal, but as long as positive half cycle, negative half cycle, both are same, this is even symmetry. This is what even symmetry. The positive half cycle, negative half cycle, both are same. No even harmonics. Only odd harmonics will generate. But among this is called fundamental. This is called fundamental. And fundamental, these are said to be lower order harmonics. Lower order harmonics. Lower order harmonics. But lower order harmonics also called dominant harmonics. Dominant harmonics. As their magnitude is more. Because their magnitude is more. Their magnitude and effect is more. Effect is more. That is the reason they are called dominant harmonics. Dominant harmonics. and rest of the things are said to be higher order harmonics. Higher order harmonics. Higher order harmonics. Higher order harmonics are less dominant. Higher order harmonics, they are less dominant. They are not much dominant, less dominant. They are less dominant. And their effect is less. Effect is less. Less effect. Less effect. Less dominant, less effect. Why? Because among third and fifth, as number of the harmonic order increases, its magnitude is going to be less. Na? Magnitude will be less. Magnitude is less. So for example, if you take, this is fundamental, say, this is fundamental. If you take 25th harmonic, how many cycle? Half cycle, 25 half cycles. 25 into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like that. This is fundamental, say, and this is 25th harmonic. 25th harmonic. How much? Negligible. Its magnitude is negligible, very, very small, negligible, neglected. Higher order harmonics will be negligible. If you are able to eliminate up to 15th harmonic, that is more than 13th harmonic is enough. 13th harmonic is enough. Higher order, the rest of the harmonics can be negligible. Their magnitude is negligible. Okay? Yeah. Lastly, there is no problem due to third harmonic, 9th harmonic, 15th harmonic, 21 harmonic, etc. They are called triplen harmonics. Triplen harmonics. Triplen harmonics. 3 into 1 is called 3. 3 into 3, 9. 3 into 7, 3 into 5, 15. 3 into 7, 21, dash, dash, dash. They are said to be, right? All these are called triplen harmonics. Triplen harmonics or zero sequence harmonics. Cophagial harmonics. They are cophagial harmonics. Cophagial harmonics. Or you can also call them zero sequence harmonics. Zero sequence harmonics. Cophagial harmonics are zero sequence harmonics. Zero sequence. And these triplen harmonics or zero sequence harmonics, they generate in the phases, but they will be eliminated in the lines. Eliminated in the lines. They eliminate in the lines. First of all, I just want to show why these are cophagial harmonics. Third, 9th, 15th, multiples of 3. Triple N, the multiples of 3, triplen harmonics. Triplen harmonics. So let me show why they are triplen harmonics. How they are triplen harmonics? See. For example, fundamental, if it is fundamental voltage E1, ER1 at an angle 0, but EY1 at an angle minus 120, EB1 at an angle minus 240, say 240. These are the fundamental, no? Fundamental. Now, what is the phase sequence of that? If you draw, this is ER1 and this is EY1, this is EB1, B1. The phasors are rotating counterclockwise direction. Phase sequence is R1, Y1, B1. This is said to be positive sequence. Fundamentals are said to be always positive sequence. Positive sequence. It may be R by B or RB, whatever it may be. Fundamental is said to be always positive sequence. Positive sequence. But whereas if you take for third harmonic, angles will be increased by n times. Angles. For example, ER3 will be 0 at an angle 3. Fundamental angle ER0. Fundamental angle ER0. 0 into 3, third harmonic. EY1 angle minus 120. Third harmonic into 3. Minus 120 into 3. And this is minus 240 into 3. And the fifth harmonic say into 5 into 5. Angles must be multiplied with n. Third harmonics 3. Fifth harmonics 5. So this is equal to how much? ER3 at an angle 0 degrees. 0. Similarly, EY3 will be minus 120 fundamental multiplied with 3. How much it will be? EY3 at an angle minus 360. Minus 360 means, can I write EY3 at an angle 0 degrees? Yes, EY3 at an angle 0. This is for fundamental, whatever I show. Third harmonic, EY3 at an angle 0. Similarly, EB3. EB3 will be minus 240 into 3. Minus 240 into 3. How much it is? EB3 minus 720 degrees. 720 degrees. 720 also equal to EB3 at an angle 0 degrees. Correct? 720 minus 720 also equal to 0. Correct? 360 degrees means from here to here again you will come to the same point. 360 degrees you will come to the same point. Okay. For example, you are here. From here to here 360 means again you will come to the same point. 720 also again you will come to the same point. That is also 0. EB3 will be 0. Now if you draw the waveform, how they are going to be? To draw this, ER3 also here. ER3, EY3, EB3, all are in same phase. ER3, EY3, EB3, all are in same phase. Then what is the phase sequence? No phase sequence for this. Phase sequence is 0. Phase sequence is 0. Similarly, ninth harmonic also, if you take ninth harmonic also, they are also same. ER9, EY9, EB9. If you do that, all they are said to be 0 sequence. This is, all this will be 0 sequence harmonics. Na? Yes. So these are said to be 0 sequence harmonics. These are the 0 sequence, 0 phase sequence. No phase sequence, not a 0 sequence. No phase sequence. That is 0 sequence. 0 sequence. Or they are said to be cophasial harmonics. Cophasial harmonics. In same phase. Cophasial means same phase. Cophasial harmonics. They are said to be cophasial harmonics. All triplet harmonics are cophasial. All triplet harmonics. All triplet harmonics are said to be cophasial. All triplet harmonics are said to be all triplet harmonics are cophasial. Okay. Not only third, not only ninth, all they will be cophasial. Cophasial. And these third harmonic, triplet harmonics will generate in the phases, but they eliminate in the lines. These points are required at the time of doing EMF equation problem. After KP, KD, I am going to the problem. You will ask star connection, what is the line voltage, what is the phase voltage? Delta connection, what is the line voltage, phase voltage? For star connection, third harmonic generate in the phases, but line harmonics, lines they will eliminate. Why eliminate means cophasial. Okay. for triplen harmonics, if you see triplen harmonics will be triplen harmonics will generate in the phases. But they will be eliminated. In the lines. The line voltages. Because they are coefficient. Coefficient. Just let me reason how. Coefficient means star connected alternator is there. Star connected alternator. So our alternator is star connected. Say. Star connected. Third harmonic will generate in the phases. Absolutely. Generate in the phases. Third harmonic generate in the phases. But coming to the lines, this is R phase, Y phase, B phase. See, EL3 is equal to ERY. ERY means ER3 minus EY3. ER3 minus EY3. But ER3, EY3, both are in same phase. For example, say ER3 is equal to some E3. That is E3 at an angle 0. This is also E3 at an angle 0. What is the net voltage? 0. Potential difference, no? Potential difference. Both magnitudes are equal and their magnitudes and phase is 0. Then what is the resultant voltage? Resultant voltage will be 0. Resultant ER3 0. EL3 will be 0. Instead of that, if you take fundamental, what is going to be happen? As a fundamental is there, na? For fundamental, they are fundamental. For example, ER1, EY1, EB1. Their line voltage is equal to EL that is EL fundamental. That fundamental is equal to ER1 minus EY1. That is equal to E1 at an angle 0 minus E1 at an angle minus 120. That is equal to root 3 into E1. This is for fundamental. Whatever I am drawing for fundamental. This is for fundamental. But third harmonic, they are 0. Third harmonic ER3, EY3, they are 0. Therefore, third harmonics eliminate. Therefore, triplen harmonics eliminate in the lines. Triplen harmonics eliminate in the lines. Eliminate in the lines. Okay. They eliminate in the lines. They won't exist in the lines. Generate in the phases. That's the reason why I am writing equation. All harmonics are there. Lines, they won't exist. Okay. Yeah. This knowledge is enough to start with short pitch winding. Okay. Armature winding, we are going to start. First distributed, short pitch winding. Fractional start winding. So next class, I am going to start with first short pitch winding. After that, we will come to the distributed winding. After pitch factor, distribution factor, individual objective questions. Later, problems on EMF equation. Okay. So, yeah. So this is the topic. So I completed today. And the next class we are going to see with another topic. Fine? Yeah. Now, any doubts are there? You please. I'm unmuting. Ask your doubts. I'm unmuting. Okay. Yeah. Bharat, tell me.
So we have used, you have shown one diagram.
Ah.
Armature winding is placed on a rotor. That is used in case of DC machines, no, sir?
No, not DC. Alternator only it can be used. DC machine definitely on the rotor only. Commutator will be there. You are connecting commutator and that AC converted to DC. But whatever diagram I have shown, they will be this one, this one.
Yes.
This one, no? Yes.
Yes.
But this is I am not using any commutator. AC only I am getting. AC generator. It's not DC generator. AC.
Do we have any practical examples for this kind of machine, sir? I don't think we use this kind of machine.
In your laboratory, this is only for small rating.
Okay.
This is only for small rating. In your laboratory, you have observed small rating of alternator. It can be anything. But large rating of alternator always it is stationary armature. Unless otherwise mentioned, alternators are always stationary armature. Generating station, if you go stationary. Small machines, order of like 10 kilowatt alternator, they may be rotating armature. Large alternators not possible. Have you observed at any time in your laboratory? In your laboratory, you can find a rotating armature, the second type, rotating armature.
Okay.
Because it is small generator, 3 kVA, 5 kVA. But large alternator, they will be always stationary armature only preferred.
And one more doubt, sir. The flux distribution.
This is clear, na? This is clear, na? This
yes,
is DC generator.
Okay, sir.
I am directly tapping the power through the slip ring end brushes.
So what I had asked is the same kind of construction is used in case of DC machines.
Yes, yes.
But
Exactly.
they use commutator.
Commutator. If you add commutator, that becomes a DC generator.
Okay.
In DC generator, voltage is how much? 300, 400 volts you will generate. Can you generate? That is the main drawback. DC generator, why can't you generate kilovolts, order of kilovolts? Commutator problem.
Yeah.
Slip rings, na? Commutator and brushes, you need to collect current.
Yeah.
That's the reason DC generator is a small voltage ratings are very less. Alternator, it is order of kilovolts. It must be, that's the reason it must be connected on the stator. Okay, next. Yeah.
And sir, flux, the diagram you have shown for flux distribution in case of cylindrical rotor.
Yeah.
But in material, they have shown a different diagrams.
No. That is okay. That strictly speaking, the number of turns can be kept up. There, the diagram shown is step to step waveform I have shown.
Yes.
By taking the each magnitude, whereas 1 to 1.
Yeah.
1 to 1, it will be its length is more actually. You are keeping the center of the pole, center of the coil, its MMF space is more.
Length it decreases from 1 dash to 2 dash.
Exactly.
So you have given whatever you have given today in notes. That's the correct one. Sir.
Yes, that's the correct.
And what of that? That is not.
That is very old one. This very old one that is related to DC machine. DC machine, you will get a similar kind of the armature MMF is a triangular wave, na?
Yeah.
You can find similar diagram, but that was kept there. Actually, not modified. It's a very old one.
So we are making flux distribution sinusoidal by this procedure. And,
yes, by distributing the winding. By distributing that statements are everything is correct only.
Yeah. So we have made flux distribution sinusoidal. So then what's the use of making this distributed winding in case of stator part? We have already achieved the flux distribution.
Good. See. Distributed means in the armature winding always distributed only. If you use cylindrical alternator also armature winding is distributed. Salient also armature side there is no difference. Armature is always distributed short pitched winding only. Distributed in the sense how I am using. In a cylindrical machine slots are there, na? slots are there. So field coils are distributed in the slots. That distributed winding is entirely different when compared with armature distributed winding. Armature always distributed only. Cylindrical also distributed, salient also distributed. What I am saying, winding, if it is distributed more slots, that you can call distributed. I am talking about rotor winding, rotor only different. Okay. Yeah. See, you may be getting confusion here. This winding I can call armature winding in this diagram. Can you able to see this? This rotor slots are made in that winding has kept. Na? Coils are not kept in only one slot. If you keep all coils only one slot, that becomes concentrated winding. Okay, DC side. But whatever I am discussing, this is armature winding, distributed pitch factor. That is large topic. Is only I am keeping in 4 or 5 slots. So that's the reason I am calling what it has the distributed winding. But whereas in salient pole machine, what we have done? Salient pole machine, this is the core. This is the core. We have kept all the coils only on the pole core. This is, I can say, concentrated. Like transformer, concentrated means if all the coils are having same axis and the same dimensions, that is concentrated. Don't think with respect to armature point of view, or if you don't want to call concentrated, simply leave it. But what is the main thing? Distributed winding in the armature, salient pole also, cylindrical also, stator winding same. I am talking about now armature winding. Armature winding always distributed in the slots.
The reason why we distribute in armature winding is to eliminate harmonics.
Yes,
Yeah.
yes.
Okay.
Harmonics. But here, can you tell me in cylindrical rotor why slots has to be done? Because on the rotor circular shape, you cannot keep any winding. There is no support for that. Compulsory, we have to cut that portion. We have to keep. But if you keep all the coil sets only in single slot, now it will become flat. Totally flat. You will get.
Okay. For flux, to get the sinusoidal flux distribution, we are making slots in cylindrical rotor.
Yes. Correct.
Okay, so that's it.
Okay. Any next unslot. Unmute and please. Do you have any control to unmute yourself? But I am unmuting all the people. Unmute and ask. Hello.
Sir, in damper winding, actually, when rotor speed is decreased, the frequency also reduces, no, sir?
Generated EMF. E correct.
Okay, sir. I mean, when rotor speed is decreased, the frequency of induced EMF also decreasing.
Exactly.
That means the RMF speed of EMF also decreasing.
RMF is due to stator currents.
That means the same frequency only, no, sir. If
Yes. That's what I am saying. Angle between E and V, E frequency different, V frequency difference. Your terminals are connected to the grid, na?
Yes, sir.
Yeah. Or else you just come from the synchronous motor. Easy understanding purpose, synchronous motor.
Okay,
actually,
sir.
Hunting topics will be discussed after synchronous motor. Huh?
Okay, sir.
In a textbook, you say hunting will be discussed in the case of synchronous motor. That is easy understanding purpose. Okay. Now you discuss about synchronous motor. Synchronous motor, first you will give the supply, na?
Yes, sir.
Supply frequency constant.
Yes, sir.
RMF constant, rotating magnetic field is constant na speed?
Yes, sir.
That speed is constant. But back EMF is there, na? Induced EMF, its frequency based on the speed, it may vary. That's the reason rotor will tend to oscillate and you will get circulating currents between those. Into the angle between E and V, that is a delta. Delta is going to be changes.
Okay, that means the RMF of stator is constant. So that to make both equal, we are using damper winding.
Yes.
Okay, what I thought is when RMF speed is decreasing, its frequency is decreasing, and again stator RMF speed also decreasing, means then both will come to same speed. No, again why damper winding? That's okay.
Your analysis is exactly correct if you take a single alternator. Like your
Okay.
laboratory
Okay.
is
As
there,
it is
na?
connected to grid, the stator frequency is constant. Okay.
Exactly, you are correct. Exactly. That's the reason I told. Hunting, all these things will be takes place. Hunting, loss of synchronism, stability, all these things will comes into picture when alternator is connected to the grid only.
Okay, sir.
Single alternator, no problem. Single alternator load increases, speed decreases. When speed
Yes, sir.
decreases, your alternator frequency also decreases.
Yes,
Your load
sir.
is accepting, you are accepting. RMF speed also decrease. Whatever
sir.
you told, that is valid for single alternator. Exactly same.
Okay, sir.
Ah.
And one last doubt, sir. One small confusion here in the EMF equation. Generally, we used to write E is equal to minus and d phi by dt. No, sir. Phi, like a circle and one line. This phi. But we are writing d psi here.
Psi is itself n into phi. You can write psi is nothing but.
Okay, flux linkages is okay. Okay, in that way, n
Flux
into phi.
linkages I am writing.
Okay, sir.
See, how many flux lines are passing inside of the coil? That is a matter.
Yes, sir.
That is a matter. So instead of simply, I want to make phi as a constant. When phi constant means d phi by dt, it is going to be zero now always.
Yes, sir.
That's the reason I am using a psi term. Psi.
Oh, okay, sir. Fine.
Right.
That's it, sir. Thank you.
Next.
Sir, in the interview, if they ask that in which mission can we give the AC supply to the rotor, in synchronous mission or induction mission? So what will be the correct answer for it?
AC for? Repeat your question.
Sir, in the interview, if they ask that in which mission, synchronous mission or induction mission, can you give the AC supply to the rotor, then what will be the correct answer for it?
Rotor, synchronous motor you can give. Induction motor we cannot give rotor. Induction motor also, rotor fed induction motor also there. Why you will apply, give the supply to the rotor? For speed control you can do it. Induction motor, stator side you will give, rotor side also you will give AC excitation. What for that is? Slip recovery scheme. Do you have idea about slip recovery scheme?
No, sir.
If you inject the power to the rotor, the machine will rotate more than synchronous speed, above synchronous speed. If you take the power from the rotor, it is less than synchronous speed. That is the concept of by using the power electronics devices. Power electronics. Do you know slip ring induction motor, rotor resistance control?
Yes, sir.
You are taking the power now from there.
Yes, sir. Yes, sir.
You are drawing the power and that power will be wasted in the resistance.
Yes, sir.
Instead of that, what you can do if you connect a AC, it is by using a converter inverter. AC converted to DC, again it is inverted to AC, it is fed back to the source. Because it's slip frequency you cannot connect directly to the grid because grid frequency 50 hertz. So in between, we need to have one connection. So what is that? So it can be converted to DC, again it is inverted to AC, it will be given. Instead of that, you can tap the power from the grid, you can inject the power into the rotor also. Slip ring induction motor, you can also give the AC supply. What for that? Speed control. Speed control. And your question is, for rotor, synchronous motor also you can give rotor supply. For which, if armature is rotating, say, I can give the AC supply. AC supply. But in interview, you need to ask perfectly. Question is, if this is I can say both can be given with AC.
Yes,
Induction motor I can
so,
give AC. Spiral
so
cage
what
I
is
cannot
more
give.
preferable?
Huh?
So what is more preferable, sir?
Synchronous motor. If it is asked to say nothing blindly, you can say synchronous motor. Synchronous motor is rotating armature, stationary field for that.
Okay.
Stationary field, rotating armature. Armature is rotating. How can you give supply to that AC to be given?
Yes, sir.
Yes. Synchronous motor.
Okay, sir.
Right. Next. Yeah. Hello. Unmute. Anyone is there? I'm unmuting. Please, you can ask. Yeah, tell me.
Sir, and 12F.
12F page you want? 12F?
I said 12F slide.
Okay.
Sir, can you please explain the 2 points, sir? I did not get that.
Which one?
Causes for harmonics.
Causes for harmonics. Actually, what we have done to obtain, we did a chamfering of the pole. Chamfering at a minimum air gap along the pole center, and air gap has increased towards the pole ends. Correct?
Yes, sir. Yes, sir.
For that, I am expecting this type of waveform, sinusoidal.
Sinusoidal.
But when you are doing in that process, most of
Yes,
the
sir.
flux will be crowded at the center. Flux prefer low reluctance path, na? Low reluctance.
Yes, sir. Low reluctance path.
So most of the flux crowded, most of the flux will prefer to flow through that path.
That path. Okay.
During that, the center of the pole also will tend to saturate. When flux density increases, center of the pole saturate.
Okay, sir.
When saturation is coming, reluctance increases. Saturation is coming means it becomes flux also constant. It won't increase.
Okay, sir. Okay.
This is what I have given.
Okay, sir.
Right. Yeah.
So then how are we converting that non-sinusoidal wave to sinusoidal wave, sir?
It is Fourier series. It is only analysis.
Okay, sir. Okay.
It is only just writing all this, because I have shown in the next slide. Now, if you add all
Yes.
these again, you will get flat.
Sir.
Harmonics is nothing but it is only mathematical analysis. But how we can make sinusoidal generated EMF means by distributing the winding. Winding is distributed and the short pitched winding. With that, resultant voltage is going to be sinusoidal. That I will prove it after completion of distributed winding.
Okay, sir.
Each coil flat top A, but 10 coils are connected in series. Resultant will become sinusoidal.
Sinusoidal.
Resultant sinusoidal. That we are going to see.
Okay.
Okay.
Yes, sir.
Yeah. Fine. So
So
anyone?
the same topic.
uh,
So here we are using a salient pole. That's why we are getting uneven flux distribution. What about
Cylindrical also you get the same thing. Cylindrical also, what will happen? Even if you take cylindrical, flux distribution is more at the center. Look, this is cylindrical machine.
because
Here
of
also, most of the flux crowded now because MMF is more there. It is like this, like this. Where is MMF is more? Here is more, na? Flux waveform. But all coils flux will be, they will give, you apply thumb rule, what will happen? Center coil also will produce a flux upwards direction. Next coil also produce flux upward. All coils are producing MMF in this direction only. This direction only. All they will be additive. But at the center, this coil is then a top coil, its magnitude is less, but it is also aiding. So these will also, here also flux distribution is more at the center of the center. Here also, even it may be cylindrical, here flux distribution is more, flux is less. This portion also will tend to saturate, this center will saturate. Same discussion. Okay?
Okay, sir. Thank you, sir.
Center also will saturate because their MMF, all flux lines are RMMF will be obtained thumb rule, all they get aiding there. So flux will be more. When you are coming towards this is there are less flux lines. Yes. Next. Hello. Hello. Yes. Yeah. I unmuted. Please, you can ask.
Hello, sir.
Hello. Yeah, tell me.
Sir, that same thing, that cylindrical rotor flux distribution, how can we say that, like, as the distance is less than that waveform strings correspondingly? So I don't get.
Huh?
Sir, like we said that the 1 dash 2 dash, the distance is less for 2 dash, like the distance varies, so the flux varies. We said that, no, sir. Cylindrical rotor case.
Okay. If I am keeping like this, stator circular shape only.
Okay.
Stator circular. If you take this is 1 dash, what is the shape of the waveform? Tell me, cross dot. How it will be?
Should be a flat waveform.
Flat wave. Correct? Huh?
Correct.
Where this much distance it will take. The coil is here and here. They will produce their MMF throughout this.
Okay.
Throughout this portion. But if you keep a coil here, okay,
Okay.
and will it produce like this? Will it also produce this much distance?
Oh no, that yeah.
The
only-
coil is here only. This is a coil. Their flux will be this much distance only.
Okay, sir. But the magnitude would be same, right, sir? For the first and second.
Okay, magnitude even though same, strictly speaking, practically
Correct.
more tons can be kept at the center. Center of the pole, they can be kept more.
Oh,
Towards the pole ends, they are going to reduce. Actually, center more number of tons can be kept. Towards this side, number of tons are going to be less.
okay, okay, sir. So
Yeah.
then one more simple doubt, sir. That when the voltages are actually separated by 120-degree phase difference, we say it's balanced. So what is the logic behind that, sir?
A three-phase machine, they must be balanced in the sense 120 degrees. Because total 360 degrees is divided by 120. 360 by 3 parts, na? Equal space distribution. R to Y, Y to B, 120. Then our generated MF also must be 120 degrees. The space displacement, there are said to be spatially state or periphery R to Y 120, Y to B 120. Correct? Huh? Or else R phase 0, Y phase 90, say B will becomes 150 degrees. Now can you get phase difference between R to Y 90, but Y to B it is 150 coming. Now it is not balanced.
Okay, okay, sir. Okay, sir.
Three phase means total 360 degrees. Now it will be divided into 3.
3 parts equally. Okay.
Only
Sir,
60 phase. For 6 phase, say 360 by 6, 30 degrees.
Okay.
For only 2 phase, it is 90. You may ask, sir, why 2 phase it is 180, 360 by 2, 180. For 180, phase angle cannot exist. 180 at a net will become 0.
0. Yeah, yes, sir.
0.
Correct.
So it could not be 180 degrees.
Okay, sir. Sir, one more thing, like what is meant by pole pitch?
Huh?
Pole pitch.
Pole
During
pitch.
pole pitch, sir.
Tomorrow we will see. Pole pitch and pole angle.
Okay, okay, sir.
Tomorrow we will see terms related to armature winding, everything we are going to see.
Okay, sir. Thank you, sir.
Right.
Sir.
Okay. Yeah.
Hello, sir.
Hello?
Sir, yesterday we have written the volume of the rotor as pi d square L, na, sir?
Yes, yes.
Sir, pi d by 2 square L, there should be, na, sir? Means cylindrical rotor is there, na, sir? Pi r square L is the formula for that.
What is that? Pi?
Pi r square L is the cylindrical rotor formula, na, sir?
Okay.
We have written, sir, pi d square L.
Proportional to.
Diameter, na, sir. Yes, sir.
Okay. And you mean to say it is a
Pi into d by
D
2
is equal
square.
to 2R. D is equal
Yeah, yeah,
to.
d is equal to 2r, sir.
Okay. Yeah. D is equal to 2R means what to do? Pi.
D square by 4 into L.
Pi D square L by 4.
Yeah, yeah.
Pi by, okay.
It should be like that. And sir, another doubt is that, sir, if we have written torque balance equation, na, sir? Torque balance equation, sir. In the RHS, we have friction and inertia and the EMF, electromagnetic torque.
Yes, yes.
Can we say that the RHS is the torque that we should supply in order to keep running in the specific direction?
Exactly. Yes.
Yes, sir.
All three forces opposing, but for making rotation, prime mover torque will be sufficient to overcome all those things. But all that equation, friction exists only running condition.
Yes, sir. Good.
Inertia also existing under running condition.
Yes, sir. Right.
Yeah. That equation valid at running condition.
Running condition. Understood, sir. Thank you, sir.
Okay. Right. Next.
Hello, sir.
Yeah. Tell me.
Good afternoon, sir.
Good afternoon.
Sir, for the silent pole machine, rotor construction is laminated silicon steel, no, sir?
Yes.
That material.
Yes, yes.
Okay. Sir, one more, sir.
Rotor stator you are saying. Rotor stator.
Rotor, sir. Rotor is made up of
Solid
laminated
steel. Solid steel.
for salient pole, sir. Machine.
It is anyhow all they will be steel only. Silicon content normally added everywhere.
But only the cylindrical is different. Only the solid steel, no, sir.
Yes. It is solid, not laminated. Salient pole rotor will be laminated.
Same as induction machine rotor.
Yes. It is also not necessary to be laminated because they are carrying the DC currents, DC currents. Will they produce any iron losses? No. But due to transient period, there may be choice of induced EMFs in the field winding that may causes. Otherwise, it is also not compulsory to be laminated.
Only normal silicon steel.
But practically it is laminated. Whenever if it is asking, say salient pole alternates laminated, rotor also. Cylindrical, not laminated.
Okay, sir. Sir, we are giving the excitation at the starting or up to end only, sir? It's confusing, sir.
I forgot to explain that point. Excitation must be given continuously.
Sir, if we give continuously, maybe that rotor is rotated, that wire may be.
Sorry? Rotor?
When we give the excitation at the starting, the rotor is rotated. At that time, when we reaches to the higher speed, can we remove that excitation, sir?
No. If excitation must be from the starting to continuously, it must be always exist. Excitation must be there always. If you remove excitation after starting, what will happen? No poles, no rotor poles. Poles will disappear. No poles are there. No poles means no question of synchronism.
Okay, sir.
It acts again. It may take place like a cylindrical. Say a cylindrical machine, salient pole machine. It acts like a induction motor or induction generator. If load is very less, say synchronous motor, induction motor, it will act as. That is the questions at the end. We are going to see what are the type of questions. I am going to do the table with table. Like in synchronous motor rotating at synchronous speed. Salient pole synchronous motor rotating. If excitation fails, then it acts as an induction motor.
Okay.
Or reluctance motor.
Okay, I thought that's a pony motor we are using in induction for twisting as well in the. Okay, sir, I got. We are using pony motor in induction motor, no, sir. For twisting that torque.
Yeah. Always excitation must be given always. When excitation is not there, say it won't act as a synchronous machine. Excitation must be given always. Excitation to be given always. It will be kept throughout the years. It has to exist. If excitation is not there, and no question of synchronous generator operation. I will tell this point. Generally, students will have a doubt in their mind like this. Excitation only given at the beginning, later, not like that. Excitation will be continuously given. Yeah.
Okay. Sir, for DC machine, we are using the separate exciter, no, sir. At that time, we can use for always, sir, excitation.
Separately excited,
Yes, sir.
Compulsory excitation has to be given always. Excitation never be opened. DC generator you take or synchronous generator, excitation must be there.
Okay, because of our labbing, in our lab, we have only a DC generator. In that, there is no excitation. That's why, sir. Maybe it's self-excited.
In your laboratory, whatever you are having, it is shunt generator or series. They are self-excited. For that, no excitation is required. But how they will get excited? Shunt winding is there, na? First,
Yes,
residual magnetism. There is some 5%, 10% residual magnetism. Now, the conditions for build-up of voltage I have studied.
Yes, sir.
There must be residual magnetism. It is an essential condition. If residual magnetism only when rotor is driven, some EMF is induced in the armature. That induced EMF armature will supply the current to the field winding. That's the reason it is self-excited. Armature of the generator is itself excited its own field.
Yes, sir.
And when field current is coming, net flux increases. When flux increases, again induced EMF, and again field current increase. Like that, it will gradually, finally, it will reach us to steady state value.
Okay,
But
sir.
in that condition also, shunt current exists or not? Shunt
Yes,
current always exists.
Sir, for armature winding, we have the different types of the winding, no, sir. For field winding, which type of the winding will use, sir? In concentrated, distributed.
Where?
In that synchronous machine only. For armature winding, we have different types of windings, concentrated, distributed. But whereas for the field winding, which we are using, sir, concentrated, distributed, or lap wave system.
It is simply DC winding. That lap winding, wave winding is varied only for armature winding. Field winding, we are keeping, see, listen. This is my, I just want to compare salient core and cylindrical. Salient and cylindrical. Salient and cylindrical, see. Yeah. This is salient pole rotor. Okay. How I am keeping winding? Winding I am keeping like this, just like this, because on the pole core I can keep. Pole core will support the pole core support for the winding. Okay.
Yes, sir.
This you can call concentrated winding. Concentrate, because there is no slots, nothing, na? Yes.
Yes, sir.
But if you take a core as a circular core, how can you keep here? Core is circular core. Can you keep the winding on the without any slots? Can you accommodate the winding? You cannot keep.
No, sir.
There is no support for that. Then what to do? You have to cut that portion. So for example, this is only, see, you just imagine it is a circular core. Circular core. How can you keep the winding on that? You cannot keep. For that, what to do? Slots has to be made. You have to cut this portion. Cut this portion. Then we are keeping winding. Okay. We are keeping winding. This is only cylindrical. But cylindrical, you are keeping more number of slots.
Yes, sir.
This is slotted area, this is unslotted area. This you please don't compare the rotor winding. It is not a lap winding or wave winding like armature winding. No. Concentrated, distributed, all the terms are related to armature winding. Here, why we are calling, simply we are distributing in more number of slots. Field winding is distributed in more slots. It does not mean it is a short pitch winding. It is, these terms are not related to rotor. Rotor is only. Totally all coils are connected in series only, na?
Yes, sir.
Even cylindrical also, salient also, we are connected simply in series. But their pole core is there, simply we can keep winding on that. But cylindrical, you cannot keep. Compulsory, it must be started, in that we need to keep. Right?
Yes, sir. Sir, one more, sir. In the starting class, we have discussed the frequency for the max higher and lower. We are making one statement 50 hertz and 60 hertz, no, sir. We are making the frequency as the constant level is the 50 hertz or 60 hertz. In that, if we use the 60 hertz, we have using the 3600 RPM. For 50 hertz, 3000 RPM, no, sir.
Yes, yes.
Sir, but we are only concentration only the 50 hertz, sir. But why not we are using the 60 hertz? Is also helpful, no, sir?
Yeah. Other countries, some countries, they are using 60 hertz also. There is not much difference. Their voltage level, current levels are different. There is not much technical differences. For example, I can also use 60 hertz also here. But where is available? Tell me. Already system is established. All our systems are generation 50 hertz and everything. Therefore, I will try to, design my machines all will be for suitable 50 hertz only. There is no separate advantages. Don't expect the 60 hertz and something totally different from 50 and if there is lot of differences, then why don't we go for 60? Already our systems are established 50. Now we cannot replace all 50 and we cannot keep 60. Na?
Yes, sir.
It's
not any technically not issue.
Not technically not much advantages.
Sir, if anyone asks 50 hertz or 60 hertz, why we are using 50 hertz? Can we say for our Indian environment we are going to the 50 hertz?
Not environment. Already the system was established for 50 hertz. Then we are going. That's all. Wherever environment means what? Is it cold, hot?
Means
they are not
environmental condition based on environmental condition.
Temperature, all these things they are not depends. Only their voltage levels, current levels are different. Frequency levels 60 hertz. There is not much. You are purchasing the systems from America. Laptop you are purchasing America. Can't use here?
Yes, we can use no, sir.
Yeah, simply adapter you can use. That's all. There is not big differences.
Okay, sir. That's all, sir. Thank you, sir.
Right. So I will close here.
Hello, sir.
Hello.
Tell me.
Hello, sir.
Sir, in damper winding, when the rotor speed is less than the synchronous speed, then how we came to know that damper torque will be supporting them, means how we got the direction of damper torque?
Induction motor torque. Again, you need to apply your right hand rule, left hand rule. So try for that.
Sir, right or left means we want to get the direction of torque, then we should apply left only.
Left hand rule. See, first you need to find out EMF. Na? For EMF, which hand you can use?
Right.
For example, this is my pole. Okay. Damper conductors are here. South pole. I am taking only one pole enough. This side will be north pole. Okay. North pole, stator pole will be there. Na? How flux direction? Flux is north to south. Okay. North to south. Fine?
Yes, sir.
This pole is rotating at what speed? Some 1500 RPM.
Yes,
But your rotor is rotating at what speed? Some 1400 RPM. Say. Okay? Rotor is rotating 1400 RPM. Now find first induced EMF first. First apply Fleming's right hand rule to find direction of induced current. Induced current. Okay. Then apply Fleming's left hand rule to find the direction of force or torque. Okay.
Okay, sir.
First apply right hand rule. When rotor is rotating clockwise, flux also rotating clockwise. Both are rotating. Conductor rotating, flux rotating. Third case I have given. Na? Do you remember? Third case. EMF
Yes,
to
sir.
find the induced EMF. Apply your right hand rule. This is the flux. Armature flux from north to south inside, but in the air gap flux is, this is the flux direction. This is the flux. Flux is in this. It is not coming outside, of course. But conductor is lower. When conductor is lower means which direction you have to assume? Opposite.
Yes, sir. Left side.
Left side. Now apply your right hand rule. This assumption. Flux, thumb motion of the conductor. What is the current? Cross, na?
Cross.
Very good. Cross is coming. Current is cross. Now apply left hand rule. Apply left hand. Flux, current inwards. So what is the direction of torque? This is the force. This is the force. Due to that, what happened? Torque is in the same direction or not?
Yes, sir.
In the same direction of rotor rotation.
Yes, sir. Got it.
If similarly, if you take 1600 RPM, in this you will get current dot.
Yes, sir.
Like that. Okay.
Sir, one more doubt. Sir, when winding is done on the rotor or stator, I mean the coils and the conductors are kept in the slots. They are bare only. Is there like nothing like shorting or sparking when the current flows through them?
Okay. No, everything is insulated. Everything will be insulated.
All the conductors are insulated.
Conductors, you mean where is your doubt? Tell me. I will come to the diagram. This one, huh?
Yes, sir.
This one. Tell me.
सर ये जो ब्लैक कलर के कंडक्टर्स पास हो रहे हैं ना, ये सब जो छोटे छोटे हैं आपस में, ये भी इंसुलेटेड है?
They will be insulated. Here, this won't touch each other. This is only minor, na? These things are minor. That I will take with a tape. A tape, separate tape can be done, and then they won't overlap. Even though first insulating tap can be kept, and everything can be tapped.
सर जो आपने एक पिक्चर दिखाई थी ना जिसमें कॉपर की वाइंडिंग्स दिख रही थी, तो वो सब तो मतलब इंसुलेटेड नहीं लग रही थी, मतलब कॉपर ब्राउनिश कलर का होता है जैसे।
No, no. From here to here, I need to keep insulation compulsory. This black color and this color is there, na? This and this, they must be insulated. You may be thinking they are overlapped one over other, both with short circuit. That is only thinking, na?
यस सर। सर एक पर्टिकुलर स्लॉट में जो वाइंडिंग है वो भी सब इंसुलेटेड रहेगी?
It must be compulsory insulated. Compulsory insulated. First insulated material I will keep. Wherever core is there, wherever core and is there, na, it must be insulated. It can be insulating material, can be kept in between this, definitely.
Okay.
Core must be compulsory insulated. Where winding is there, na, kept on the core, not only this machine. General principle, blind thing is, core is also steel. Steel also conducting material, na? Compulsory,
Yes,
the insulating material must be placed. First insulation will place, in that conductor will place. I am not showing this every time because our topic is very huge topic, na? These things I cannot explain. It is understood. That's the reason at the time of armature winding I have shown, na?
Yes sir.
Even transformer also insulation is there or not? Compulsory.
Yes.
Core steel, magnet also conducting material only. It is not insulated. Windings are copper. It should be.
Okay sir. Thank you sir.
Yeah, right.
Hello, sir.
Tell me.
Sir, the winding combinations. Sir, yesterday's topic.
Tell me.
Sir, how the winding connections are made on the poles actually?
Pole?
Sir, winding connections. How
it acts as a north pole, how it acts as a south pole. That is your doubt, huh?
Yes, sir. Yes, sir. Yes, sir.
Okay. Okay. See. This is a pole. Okay. Yeah. On this winding, there are sense of the winding. How I am winding clockwise direction.
Yes.
See, clockwise means is the core. I am starting this side. So compulsory we have to wound like this. You start compulsory. Here you see. This is sense of the winding is clockwise. Clockwise sense of the winding. Clockwise. This is counterclockwise. Counterclockwise. Counterclockwise means you are started outside, that side, reverse side, not your side. Are you getting it? This is coil.
Yes, sir.
I am starting at a counter. You are started that side means compulsory we have to wound the winding has to be kept around the core. So for these two cases, how the pole will sound? Apply your thumb rule. Thumb rule means entering, leaving. Flux it is giving flux outwards. That as an north pole.
Okay.
If same thing you want to operate as a south pole, what you will do? Change the polarities. Plus minus is there, na? You change minus plus, current direction changes. Then it is going to be south pole. North becomes south.
Yes, sir.
And similarly here also, here it acts as a south pole. It will take the flux. South pole. See, south to north, all these are. First, while we are manufacturing, what we will do? First, all coils will be wound in one particular direction. First, we will fix it to the stator. Now, I will check this north pole. This should be south pole. If it is also acting north pole, say simply I will interchange the beginning, ending. North becomes south. Okay. Right?
Okay, sir. Means by changing polarity, we can change the pole direction.
Yeah. That's all. Okay.
And sir, one more doubt. Sir, we have used the short pitch distributed type winding. Sir, can we use any other combinations of winding? Means what will the performance on our system if the winding combinations are changed?
Effect on what? Performance?
Performance of our means generator. What will be the impact on the generator, sir, if winding combinations are changed?
Winding combination means what is the combination? Distributed full picture you want, correct?
Yes, sir. Such kinds of means.
Distributed winding with that some harmonics eliminated, but full pitch winding, no harmonics eliminated. But if you distribute and short pitch, distributed winding also eliminate some harmonics, short pitch also will eliminate some harmonics. Like effectively, combined effort,
Yes, sir.
by doing all those things, all harmonics will be eliminated.
Okay, sir.
Only distributed short full pitch, say distributed winding will participate to eliminate harmonics, but full pitch winding it won't eliminate any harmonics. Then you are not eliminated maximum number of harmonics, no. So compulsory distributed short pitch means practical machine, your generated EMF is pure sinusoidal.
Okay, sir.
Okay, right.
Thank you.
Hello, sir.
Hello.
Sir, in how we are getting flat waveform in that 1 coil, sir? Hello.
See, this is one coil I am keeping, na?
Yes, sir.
1 dash. How you will get? Tell me. The crossed. Flux is equal to MMF by reluctance.
Yes, sir.
MMF is constant. Why DC? MMF
Yes, sir.
is what? Ampere turns. Current is constant. Air gap is constant. Na? From here to here, air gap constant. I am not drawing the stator. Okay. So now you will get, by this it will be like this.
Then why in 2 dash it will decrease, sir? Width will decrease.
What is the space?
Here it will be more.
See, if I am keeping here, do you expect the same distance will come? See, this coil, this is one combination. 1 to 1 dash.
Yes, sir.
This is some 3 dash, say. Okay.
Yes.
When coil is this much, how can you produce flux in all other way? When coil is there, this is the coil. It will produce flux inside of the coil only. If coil is
Yes,
bigger
sir.
coil, it will produce the MMF throughout that coil. Okay.
Yes, sir. Yes, sir. It is with respect to space we are drawing, na, sir?
Space, exactly.
Okay, sir. Okay. Sir, one more doubt, sir.
This coil space is more. This coil diameter is more, na, here. But
Yes,
here,
sir.
yeah, its width is less. Yeah.
Yes, sir. One more doubt, sir. Related to that magnetic drag, sir. We are defining magnetic drag when we are taking armature conductor on rotor, sir. But if we will take armature conductor on stator, then how magnetic drag will be there?
Yes, everywhere it will take place.
Sir, can you explain, sir? I am not getting that.
Generator, no?
Yes, sir.
See, this is rotor. This is a conductor. Okay?
Yes.
One conductor, let me take enough. Say this is North Pole. North Pole. Or South Pole. You want to take North or South?
So any you can take north or south.
North Pole. Okay. By North Pole, what is the flux direction? In this direction. I am not taking
Outward.
another pole. This is the direction. Okay. Okay, na? Rotor is rotating in clockwise direction. I am rotating my rotor clockwise direction. Clockwise. What is the current in this? Current will be cross. Correct?
Cross, sir. Yes, sir.
Current is cross. Okay, cross. Now when current is coming cross, current interact with the flux, it will
Yes,
develop
sir.
the torque. To find
Yes,
the
sir.
torque, apply our left hand rule. This is prime mover torque. This is the prime mover torque. Due to prime mover torque, rotor is rotating in clockwise. Correct?
Yes, sir.
Yes. Now, EMF is induced and current you are getting cross. Now, what is the torque by current? forefinger, left hand rule, apply left hand rule. Left hand rule applying forefinger flux direction, center finger
Current direction.
Center finger current direction, thumb shows force direction, correct?
Force. Yes, sir.
Flux is like this only. Current is inwards. Force on the conductor. This is the force on the conductor. Force on conductor. Left hand rule. Forefinger flux. Center finger current. Thumb shows force on the conductor.
Conductor.
But what is the force on the conductor? Cannot rotate, na?
No, sir.
Conductor cannot rotate. But it will develop the equivalent torque on the equivalent force on the rotor. Which direction? Opposite direction. Force on the rotor. Force on the conductor, stationary conductor right side say, equivalent force on the rotor will be reverse.
Why, sir? Not getting this point.
That is itself left hand rule, na?
Sir, this I got that force on conductor will be in rightward, sir. Then how it will affect that on rotary it will be in leftward, sir.
Rotor won't rotate left side. Prime mover torque is greater, rotor is rotating clockwise only. But
Yes,
electromagnetic torque it is opposing opposite direction.
Sir. It will be mainly due to because of that current there will be magnetic field. And that field will oppose the main field.
You want detailed explanation, huh? Okay.
Yes, sir.
You spare some 15 minutes? Yeah. Okay. This anyhow that I am going to explain at the time of synchronous motor torque production. Torque production, see, or else wait for some. You have asked, na? Therefore, I need to explain. For that, your practical, these things are, but if I explain all these things, we never complete our synchronous motion. See, okay, this is north pole, south pole, north pole, south pole. Okay, I am talking about synchronous motor. See, or generator, let me take generator. I will rotate this with prime mover. Which direction? Clockwise direction. Rotating prime mover in clockwise, no? Yes.
Yes, sir.
This is one conductor, one conductor, one conductor, one conductor. You take. Okay. When flux is in this direction, this is the flux direction. On this, of course, this will take a return path like this.
Yes, sir.
Fine. Now, when rotor is rotating in clockwise direction, tell me what is the current produced that will be?
Cross, sir.
Cross. Good. Cross. In this dot, here it will be cross. Here it will be dot. Okay? Dot. Once current is coming, which type of you apply? Poles, stator also poles will form, na?
Yes, sir.
To find the poles, apply thumb rule. Current is entering, current is leaving. So due to this, it will produce the flux. Correct?
North.
This one. Which pole will form here?
North. Oh, sorry, south pole.
South pole will form.
Yes,
sir. South pole. Similarly, here which pole will form? This is the flux coming. North pole. Good. North pole. This here it will be south pole again. South pole. Here it will be north pole.
North pole.
Okay.
Yes, sir.
Yes. See now. This is the north pole, south pole. This is south pole of the stator poles. They will also rotate. Why? Because their frequency is there, na? RMF rotating.
Yes, sir.
See. Now, when rotor is rotating here, okay. Then south pole is lagging, no? Rotor is rotating in clockwise. All rotation is in clockwise. South pole is backside. What south pole will do?
Attract, sir, it.
Attracting in this direction. Now torque by stator poles. The stator current are producing stator poles. They are developing a torque on the rotor. South pole attract. Okay.
Yes, sir.
And the south pole repel the south pole, rotor pole. North pole of the stator attract the south pole. This north pole of the rotor repel this north pole. South pole attract. South pole repel.
Repel.
North pole attract. It's not. Then what is the direction of torque? Counterclockwise.
Counterclockwise.
Counterclockwise. Correct? Yes.
Yes, sir.
Your electromagnetic torque is counterclockwise direction. Okay.
Yes, sir.
Now you apply your left hand rule. Left hand rule. On the first conductor, cross conductor, flux direction. This is the flux. Current is inwards. What is the force on the conductor?
Downwards.
Force on the conductor downwards. Okay. Left hand rule shows forefinger flux direction, center finger current, thumb shows force. Force on the conductor downwards. But conductor cannot move, na?
Yes, sir.
It is not free to move. But the torque effect will be there. Equivalent torque on the rotor will be reverse direction. This is what I have here. Upwards.
Okay, sir.
That's what you now. If you take it with respect to poles attraction, you are happy. Correct? That is what going to happen. Remember that whenever you are applying left hand rule on a stationary conductor, the equivalent force on the rotor will be reverse.
Okay, sir.
Because ultimately rotor is free to rotate, na?
Yes, sir. Yes, sir.
So effect on the rotor will be reverse. You have to take opposite direction because conductor is not free to rotate. You can check everywhere; it will be valid.
Okay.
Right.
Thank you, sir.
Next. Yeah. Hello, anyone? Okay, I'm stopping the session. Any doubts are there? You please answer.